say is that I'll be here all week through the end of the event. So if any of these things that I talk about, I'll drop a few open questions here and there. If it sounds interesting to you, I'd love to talk with you about it. Come seek me out. I'll have time. Okay, good. So what I'm talking about today is the forbidden structure method in graph metric sparsification. There's a lot of words in there which kind of narrow down the scope of what I'm about to talk about. So let me start by getting that out of the way. So this gray box right here, this is like the template theorem that we care about in graph metric sparsification. We want to prove theorems of the form, for every graph G that you might give me, there is some other graph H that approximately preserves certain distance or reachability information of G. And additionally, we want H to be very small, ideally much smaller than G was originally. It's a sparsifier. We're like making things smaller without messing up the important properties of G too much. So here's by far the most famous example of what I'm talking about. There is one particular graph metric sparsifier that is considered so important that we teach all of our undergrads about this, and it's the only object like that. That object is what I'm going to call an S cross V distance preserver. So what that is you get some graph G on input, and you get some distinguished node S, a source node. And your goal is to come up with a potentially much sparser graph H, like the one on the right, just those red edges, which preserves the shortest path distance from that given node S to every other node in the graph. So for example, from S to this node, the shortest path distance is 2 by several different paths. Over here in H, even though we've removed a bunch of edges, shortest path distance is still 2. So the sense in which H approximates G is that only some of the distances are preserved, but it's potentially much smaller, and we consider that a win. And the sense in which it's smaller is that we can always construct one on n-1 edges. One thing that I want to say about this, though, some people call this problem BFS trees or shortest path trees or something like that. And so if you're thinking of that, you're right. That is what I'm talking about here. But I don't like that name for it. That name spoils the punchline. Because there's an important thing about this problem, which is that you can make it a tree, that single source distances map onto trees. And kind of the key point of this talk will be to think of that not as something that was given to you in the problem, but as an important discovery that generalizes to other objects. So I'll say what I mean by that. Let me just do sort of my quick history or applications before we really get into the objects themselves. So graph metric sparsifiers, they were implicitly studied throughout basically the 60s to 90s mostly. They were used in the background whilst studying other objects or algorithms or something like that. Then they were abstracted throughout a series of papers in the 90s where these objects were kind of defined and studied more in their own right. Some of the things that they were used for, one really common use case is algorithmic preprocessing. That one especially persists to this day. The idea is that if you were to use H instead of G when running an algorithm, you might take on a bit of error in your algorithm, but because H is smaller, it will go much faster. Another common use case for these things is network design. The idea is like, if G is the network that you want to build, but then you went through some budget cuts, or maybe you don't have enough memory or something like that, you could choose to build H instead, and it's much cheaper, but roughly as good as the original. The last application that I'll mention before forgetting about applications forever is distributed protocols. This was really a major use case that got these things off the ground. The idea is that you could, if G is like a large communication network, you could dedicate some of the edges, like just H, to pass information around the graph, maybe some specific type of information, and then you know that you haven't really lost too many edges, but all the nodes might roughly agree on some important quantity. This is often used for something called synchronizers, where they pass around clock time. That's one example, but there are more. So having kind of done service to the algorithmic problems that motivate these, I'm now going to spend the rest of the talk on the object themselves. Okay, so here's what we're doing today. Within this area now, if you're like somebody who is like really working in this area, there are two different sets of techniques that people commonly use. Sorry, was there a question? Oh, yep. There are two different sets of techniques that people commonly use. One I'm going to call graph clustering and decomposition methods. The other one I'm going to call forbidden structure methods. And these each have pros and cons. Like with these two sets of methods, and there really is, to my eye at least, a split in the papers in the area between these areas. They each have pros and cons. So a pro of the graph clustering and decomposition stuff is if your number one goal is to compute the object quickly, you want like a near linear time algorithm or something like that, decomposition methods are really effective. The first thing you do is often a low diameter decomposition or an expander decomposition or any of these other buzzwords. On the other hand, if maybe you don't care quite so much about computation time, but you're really just trying to optimize like the size of the sparsifier that you're building or the trade-off between error and size or something like that, the forbidden structure methods have the advantage there, I would say. They tend to get better bounds and tend to do it a bit more simply. Another thing, an advantage for graph clustering and decomposition, I would give that one the edge in ties to other areas of computer science, like graph algorithms. Decomposition and clustering shows up a lot. Meanwhile, I would give the forbidden structure methods, related to that, they kind of have an advantage in simplicity. They're often very self-contained. You don't need to know a lot about what's going on in the rest of computer science to apply these so much. Last one, the underlying mathematics of clustering and decomposition is what I would call graph metric theory. That tends to be what it draws on. The one on the right tends to draw on extremal combinatorics. So having said all that, there are these there's the red team and the blue team that are sort of all proving results about this. Yes?
Yeah, so forwarding structure, is it like forwarding subgraph or forwarding minors or forwarding what?
Oh, for forbidden structures?
Yeah.
Good, I'll say a little bit more about that in a second. I mean all of the above. So it could be forbidding subgraphs, it could be forbidding minors, it could be a few other things as well.
So at the moment you're talking about unweighted, right?
Sorry, what's that?
At the moment you're talking about unweighted something.
It could be either. So all the examples I've given that I've put up in figures were unweighted graphs, but most of what I say today will apply to both. Okay, so having said all that, we are now going to join the blue team. So the rest of this talk is pretty much going to forget about graph clustering and decomposition. It's good stuff. There's great papers going on out there about it. But this is a talk about forbidden structure methods, specifically. It's going to be a survey. I'm going to go through a bunch of papers. It's a bit of like a self-serving survey because I'm excited about this area and I want to like eventually get to some papers that I have in it recently, but that'll be more towards the end of the talk. Okay, so having said that, I'm just going to sort of slowly introduce these forbidden structure methods and see what they buy us. So I started with this S cross V distance preserver thing, which I was like, this is BFS trees between me and you, but like don't tell anyone that that's what's going on here yet. So here's the official definition. I won't repeat it, it's the same one that I said before. And the folklore theorem that maybe we all know is that you can always construct one of these single source distance preservers on at most n-1 edges. Now, out of the many proofs that you might have seen in the past, it will be important for this talk to focus on the following proof. So two things. One, I want to point out that there's this very natural greedy algorithm that obtains it. And what that greedy algorithm does is it just goes through the edges of G in some particular order, whatever it says in blue there, and it greedily decides whether that edge looks necessary based on the current state of H to include in the graph. So first we would look at this edge, we would be like, the distance in G is 1, the distance in H was infinity, but now we have to add the edge to correct that. Then we do so for the next edge and choose to add it, for the next edge, and then we go to the later edges, add those. Eventually we reach this moment where this edge is the next one to be considered, and we'll see that adding that edge would not, in fact, affect the shortest path distance from H to its endpoints, so that one is safe to, I guess that edge, but that one is safe to skip, as well as that one, as well as that one. But all you really need to know from this is, A, there's a very simple greedy algorithm that's like instantly correct, that constructs this. The only question on the table is how we show that it always returns a sparse subgraph. And the way that we show that is with this indirect structural method. What I mean by that is that the lemma that you prove in order to certify that H is sparse is you don't directly say H must have n-1 edges. Instead you say H will not have any cycle subgraphs. If you look at this, it's a tree, it doesn't have any cycle subgraphs, and you can prove on structural grounds that that will never happen. It can't have cycle subgraphs. And once we've done that, now we can just apply this like black box theorem from extremal combinatorics. It's a relatively easy theorem from extremal combinatorics, but nonetheless a theorem from extremal combinatorics. that says the maximum possible number of edges you can have in a graph without cycles is n minus 1. I'm sort of doing this as an excuse to introduce some notation, so let me point at that. This phrase right here, x of n and then c less than or equal to n, that is something called the Turan function. X stands for either extremal or excluded, depending on who you ask. But one way or the other, the meaning of that phrase right there is this is the maximum possible number of edges in an n-node graph that avoids all subgraphs in this list. So c less than or equal to n is my shorthand for all cycles of length n or less. Okay, cool. Takeaway here is not to shock you with the existence of single source distance preservers. It's this two-lemma split right here, because that's going to show up over and over through the talk. You indirectly bound the number of edges. Okay, so to reinforce that, the next object that I want to say one more thing about these, and then I'll move on. I want to point out that there's also lower bounds. So the structural upper bound is that these distance preservers don't have cycles. The corresponding structural lower bound is that if I were to give you a graph such as H that doesn't have cycles to begin with, no edges could possibly be removed in one of these single source distance preservers. And that kind of gives you a reduction on both sides. It tells you that the right bound is exactly this x of n cn function that we're talking about.
So is it somewhat interesting that a non-existence result is giving you an upper bound?
Oh yeah, so the fact that no subgraphs implies some sort of upper bound? Yeah, definitely. So there's a lot of kind of strange mathematics around that. That's kind of going to be what I focus on in the second half of the talk, is how that all works. For now, I'm going to mostly black box those. But yes, you're absolutely right. There's something interesting there. Good. Everyone else good so far? Cool. Okay, so the next object that I want to talk about, where now, having seen this template once, I'm hoping will be helpful, is a spanner. So a k-spanner of a graph is some subgraph that preserves all pairs shortest path distances, so unlike the single source distance preserver now. But the sense in which it's an approximation is that there's this parameter k. There it is. There's this parameter k, and you only have to preserve your distances up to a stretch factor of k. For example, if we look at this input graph G, this pair of nodes has distance 1 right here. If we look at the corresponding pair of nodes on H, it has distance 3. That is a factor of 3 difference, which is compatible with the claim that K is a 3-spanner, that H is a 3-spanner. To be totally thorough, we would have to check that on all pairs of nodes, but it'll work out. Okay, so we would ideally like to construct sparse spanners, and the state-of-the-art result is from this classic paper from 1993, and it shows the following bounds. If you want a 2k minus 1 spanner, you can always get that on about n to the 1 plus 1 over k edges. And the really cool, smart thing about how they went about proving this theorem is that it's like an exact analog of the shortest path tree algorithm and proof that we just saw. So here's what I mean. So we're going to do this greedy algorithm, and it's basically the same. We're just considering the edges. There we go. We're considering the edges of the input graph in some predefined order, and we're going to look at each edge and greedily decide whether or not it seems necessary at the moment that it's inspected. For example, we look at this edge, the distance between these nodes is 1 in G and it's infinity in H, so we would choose to add that edge to the spanner. Then we would look at this edge, its distance is 1 in G and infinity in H, so we would choose to add that edge to the spanner. For the same reason, we would add that edge and that edge. And now when we inspect this last one, we see that the distance is 1 in G and it's 3 in H, which is acceptable. So the greedy algorithm does not think that this edge is necessary and it would throw it away. Okay, so that's an example of the greedy algorithm. It's basically the same as the one for BFS trees, just with the 2 phrases in blue tweaked for this specific problem. Question?
Could you just go back to the last slide once?
Yes.
The previous slide.
Oh, sorry, hit the wrong button to go back. There we go.
Okay.
Cool.
Right now it's unweighted, so you can consider the edges in any order.
Yes, you're absolutely right. So because this example that we're looking at is an unweighted graph, it totally won't matter what order you consider the edges in. That order thing is only going to matter if it's a weighted graph. Okay, so the cool thing about this proof, or what I like about it, is that it does this same indirect controlling of the number of edges that wind up in the spanner. Which is to say, instead of trying to kind of directly prove some bound on the number of edges that show up in H, what it does is it proves that this output spanner is never going to have any small cycles as subgraphs. So before we were saying it has no cycles at all. Now we're making a weaker claim. We're just saying that it doesn't have cycles of length 2k or less. For example, there's a very prominent 4 cycle going on in this input graph. In this spanner, we did not complete the 4 cycle. We threw away the last edge. And we kind of didn't complete it because of the 4 cycle. The rest of the 4 cycle is what provided the alternate path that let us throw it away. And it's always going to work like that. We're always going to choose to not complete cycles for that reason. That's what this lemma one is saying. And now that we have that, we can then add on as lemma to this high-powered black box extremal bound from extremal combinatorics, which says any graph at all, I no longer care that it came from this greedy algorithm or from anything else, any graph that lacks short cycles like this just must be a sparse graph. It can only have order n to the 1 plus 1 over k edges in it. There is a, yes, question?
So, second part of the algorithm, right? Like, if the distance is greater than 2k minus 1, you're adding that may form a cycle.
Sorry, so if the distance is greater and you choose to add the edge? Yeah, so this is true. So you could form a cycle from adding that edge, but you'll never form a short cycle from adding that edge, is kind of the point. So we're only claiming that we don't have cycles of 2k or fewer edges in them, but we could totally have cycles of more edges than that.
This is like large girth graphs as well.
Yes, exactly. So another name for graphs that don't have short cycles is a high girth graph. Yeah?
So in the second line of the algorithm, in the case of weighted graphs, it's possible that the distance UV is coming from some other path rather than an edge. Why does adding the edge helps?
Sorry, could you repeat that last part?
I'm saying that the distance in the second line, it's possible that the distance G between U to V in a weighted graph can be from a path and not this edge. So why does adding this edge helps?
This is true. So if that's the case, it turns out to be a special property of this algorithm that if the distance in G from U to V is being realized by a path rather than an edge, you can prove that this algorithm will never actually choose to add that edge. You can do something like go along that previous path and show that you have a reasonably good hop path from each of the edges that were previously considered. It's a bit non-trivial. You have to do some analysis there, but it'll work out that way. Other questions on this so far? Okay, I do want to foreshadow something that's coming in this talk that's a little bit subtle. When we did our single source distance preservers, this lemma 2 was giving us an exactly tight extremal bound. We had that x of n cn was exactly n minus 1. Here I'm only claiming an upper bound, and we don't actually know whether or not that upper bound is tight. That's something I'm going to talk about a lot going forward. But this is only an upper bound. You can asymptotically improve that upper bound for any k. You will become famous in math and combinatoric circles. That's the biggest open problem in the area. Okay, so having said that, I'm going to sort of keep rolling. I want to make one point related to that, though. So we have this structural upper bound that 2k minus 1 spanners are really all about forbidden 2k or smaller cycles. That's what I'm calling the structural upper bound. And just like we did for the distance preservers, we have a matching structural lower bound, which is to say if you give me some input graph that doesn't have any of these short cycles in the first place, and I'm treating that as unweighted, then no edges can possibly be removed from that input graph in a valid spanner. For example, if we were to look at H and treat that as an input graph for a moment, no one of these edges is removable because you'll stretch the distance from 1 to something more than 3, in fact, infinity in this case. Good. So what that tells us together is that the best possible bound for spanners, for 2k minus 1 spanners, is exactly that thing. It's x of n c of 2k. It's just that we don't know what that is. The value is unknown, but we do know that that greedy algorithm and that extremal bound are both optimal. Okay. So that's what I have to say about spanners. Here's our story so far. We have like tight structural reductions for the first two objects that we've looked at, but they differ in whether the known extremal bounds associated to those forbidden structures are tight or not, or whether it's an open question in extremal combinatorics to pin down the right bound.
The edge efficiency of that algorithm would actually give you, like if you prove that the algorithm say terminates in by selecting less than, or then you would prove that this bound is tight.
Yeah, absolutely. So because of this tight connection, if you were to somehow do some like nice algorithmic analysis to show that that particular algorithm produced small spanners, that would be good enough to improve this thing in extremal combinatorics. Yeah?
What is the best lower bound node?
Good question. It's very complicated, and I tried to write it down, and then it like took up most of the slide. It is of the form n to the 1 plus 1 over some constant times k. So theta of k, I guess, in the denominator, but being more specific than that is tough.
So this is assuming the God conjecture, right?
No, so the girth conjecture, I'll talk about that in a bit. The girth conjecture is the conjecture that this bound is tight, but it's not known whether or not that's the case except for a few specific values of k. Other questions so far? Cool. Okay. So just quick note, I guess this is the lower bounds that I was mentioning. Oh, that's because I just clicked the wrong direction on the slides. There we go. Okay, just a quick note on another couple of objects that I'm not going to talk about, but to which these forbidden cycle methods, very similar to what I just talked about, also apply. There's an object called light spanners. These are exactly like the spanners that I just talked about, but instead of the goal being to minimize the number of edges, the goal is instead to minimize the total edge weight that you take into the spanner, where in this case, edge weight is normalized by that ratio. It's the weight of the spanner divided by the weight of the minimum spanning tree of the input graph, which you think of as like what you have to pay anyways just to maintain connectivity. So this is another commonly studied problem. It turns out to be useful in traveling salesman algorithms, among other things. But there's this nice paper I want to kind of shout out as being very relevant to this talk by Elkin, Neiman, and Solomon from 2014. It was an ICALP. And what they did is they basically showed the analogous reduction from 2k minus 1 spanners that are trying to be light rather than trying to be sparse to graphs with a specific type of forbidden cycle. That type of forbidden cycle is cycles whose total weight divided by the max edge weight on the cycle, this notion of normalized weight, is at most 2k. So for example, if you have that cycle in your graph, the normalized weight of that cycle is the sum of its edges, which is 10, divided by its heaviest edge, which is 4. And you would forbid cycles through which that quantity is too low. That's how their reduction worked. I'm not going to say more about it, just want to say that like these methods extend with fancier techniques beyond what I'm talking about. One other is fault-tolerant spanners. The basic idea behind fault-tolerant spanners is, for example, a vertex fault-tolerant spanner is one that is still a spanner after a small number of vertices fail in both the spanner and the original graph. And it turns out that through this kind of, by now, pretty long series of papers, you can reduce vertex fault-tolerant spanners as well as some other fault tolerance notions like edge faults or something called degree faults or color faults to the same sort of cycle-free notions. Okay, not going to say more about that, but like if this direction interests you, this is kind of just supposed to be a couple places to look. Is there a question over here? Yeah.
So the first one, light spanners. Why isn't the objective just minimize weight of edge? I mean, isn't G just a fixed graph?
Oh yeah, good question. So the reason why the objective here is not to minimize the weight of H is if we were trying to come up with an algorithm that minimized the weight of H, that would be a totally reasonable objective for us to have. In fact, it would basically be the same objective, like you're saying. But that's not quite our objective. Our objective is to prove worst case bounds. Okay. In the same way that on the previous one we were saying the worst case bound is n to the 1 plus 1 over k edges in your spanner. And for that reason, the weight of H can be unbounded just by scaling up the weight, so you have to normalize by something.
Okay.
Other questions? Yeah.
Sorry, for unweighted graphs, is this the same as the cycling conjecture, is it? Because the maximum weight is of an edge in the cycle is 1. So it's...
Yes, exactly. So in the special case of unweighted graphs, this condition is the same as just saying the graph doesn't have short cycles, just like before.
So, do fault tolerance values exist for all values of the field? When do they exist in the first place?
So they exist for all values of f. Any graph is automatically a fault-tolerant spanner of itself, so you're guaranteed that one always exists in sort of a trivial way. But there are non-trivial bounds for f all the way up to n for vertex faults. For other objects, it's a little bit more complicated to state. Yeah?
What do we exactly mean by the fault-tolerant notion? Like the vertex itself is not part of the spanner?
Oh, good. So what this is for any set of at most f vertices, if you delete that from both the original graph and from the spanner, then the remaining part of the spanner is still a spanner of the remaining part of the original graph. There are other fault tolerance notions that don't quite work that way, but that's the one that I mean on this slide. Other questions? Cool. Okay, so let me roll on to a few other objects, which I will say a bit more about than whatever's going on this slide. Oops, keep going the wrong way. So the next one I'm gonna sort of like expand our list of techniques that can be used to prove forbidden structure theorems. In order to do that, the next thing I want to talk about is a distance preserver. So a P distance preserver, I'm calling it that to distinguish from an S cross V distance preserver, which we talked about before. This is like, instead of just being given a node and having to preserve distances from that node everywhere else, we are instead given an arbitrary set of demand pairs, which is what's represented by that capital P. It could be absolutely anything. And the goal is for the subgraph to preserve distances among those demand pairs. For example, what's going on in this picture, we can imagine G being an input graph. It's directed with everything kind of directed southeast. And there's 4 demand pairs, which are color and shape coded here. For example, those 2 red endpoints are supposed to be one demand pair. The 2 blue squares are supposed to be another, and so on. So you can then check that H, despite missing most of the edges, exactly preserves the shortest path distance for each of the 4 demand pairs. Okay, so this is the next object that I want to talk about, and I'm going to tell you about 2 theorems, or 2 bounds that are known for these things. The first one is by Coppersmith and Elkin from a classic SOTA paper of 2006. What they proved is that if your input graph is either undirected or a DAG, then this thing, which I won't read to you, but this somewhat complicated bound is it's the best known to this day upper bound on the size of these things. And then there's another theorem, which is like kind of half from that same Coppersmith-Elkin paper and half from one of my papers from a while ago, that says in the directed setting, you get a slightly worse bound. This n to the 1/2 changed to an n to the 2/3 is the only difference here. You get a slightly worse bound, but still something nice. Okay, one thing, I'm going to go on a quick tangent here. Something that's interesting about these bounds is the following. So we talked about S cross V distance preservers, and there was this punchline that you could preserve n distances using only a linear number of edges. You only needed ordered n edges in your preserver. So think for a moment, like if you've heard that fact before and it's been sold to you as something fundamental that you should know, think about how cheated you would feel if it turned out that actually if you had any n arbitrary demand pairs, you only needed order n edges in order to preserve those distances. That'd be really interesting, right? If this like structural fact that you had been sold all your life wasn't actually necessary. Okay, so if you can like imagine how cheated you would feel with that, it turns out you should feel square root that cheated. So the number of demand pairs that you can preserve, if you have up to square root n demand pairs and you plug that into this thing right here, it's saying you can have a distance preserver on order n edges, which is kind of a surprising fact, I think. Like 1 demand pair could already cost you n edges. Now I'm saying you can go all the way up to square root n with no real additional cost. This is also tight. If you try to make this claim for any larger range of p, like p being square root n log n or something, it becomes false. That's what I mean by tight. On the other side here, for directed graphs, it turns out you only have to feel cube root is cheated for this one. So if you plug in p being cube root n here, you're going to get a bound of order n, which is kind of interesting. But a good open question in this area is whether or not that range is tight. It is conceivable that many asymptotically more demand pairs than that, in fact up to square root n, could still only cost you order n edges in the directed setting. This is just an open question that has not been proved or disproved yet.
Single like S cross V, like, the number of demand pairs were n, right? Like for S and every other.
Yes, exactly. That had end-to-end pairs. Cool. I think this is like there's a few other related open questions that I'll go through, but I think this is one of the really nice open questions in the area is how many demand pairs in a directed graph can you always preserve distances for using only order n edges? Okay, now let me tell you how you actually go about proving what we do know and how you get these like non-trivial linear thresholds in each case. So one thing that I want to like point out is that construction algorithms for these objects don't actually have all that many decisions to make. All you're really doing is taking one shortest path per demand pair and sticking those on top of each other. And the only potential decisions you have to make are in the case of ties. For example, if we start by looking at that red demand pair right here, there's a unique shortest path, in fact a unique path of any kind, for that demand pair in the input graph. So you have no choices to make. You just have to take all the edges in that path into your preserver.
In
Sorry?
the previous slide, that also for DAG, this is type, right? The square root of
Yes, also type for DAGs. Yep.
But unlike case spanners here, you're looking at exact distance.
Right, there's no approximation allowed. You must preserve distances exactly for this problem. Okay, cool. Okay, so for that red pair, unique path, you must take it. You have no choices to make. That green pair, for example, as well as the others, you do have choices to make. You could either take this southern shortest path or this northern shortest path. Both are allowed. And the way to think of it, I guess, is that you generally want to take whichever one is going to let you reuse edges. Let you have some edge that's going to play double duty in several shortest paths so that you don't have to pay for it twice. So with that intuition, if that feels right to you, if your adversary is providing you with a hard instance, what you should generally expect a hard instance to look like is it would be one without ties, because that's not giving you any freedom, and one where the shortest paths don't overlap, they're edge disjoint from each other, so that you truly have to pay for all of them. In fact, that intuition turns out to be correct. This was a relatively recent thing to have been formalized, but it was kind of bubbling under the area for a while. It's called the independence lemma. I'm going to describe it that way through the talk. What it's saying is basically, when constructing these things, you can assume without loss of generality that your demand pairs have unique edge disjoint shortest paths. And if you can prove some bound in that setting, you get a bound in the general setting. This, by the way, invokes some greedy algorithm that's analogous to the ones I've been talking about. So that's where the greed is all hiding for this problem. Do you have a question?
Yeah, and I had a question in the previous step. Can you upper bound the predistance preserver in the case of weighted graphs? Weighted and directed graphs?
Yes, good question. These results that I put up here, these are in the weighted setting. They both hold for weighted graphs. Cool. Okay, so, oh yes.
So what we can do is we can put all of the shortest paths, not only the not a single one, all of the possible ones, and then at the end check in which one, if we remove, we are paying the least cost or something.
Yeah, do you mean for the sake of this independence lemma?
No, for constructing this predistance preservers, so just instead of breaking shortest path ties as we go on, break it at the end after putting all the shortest paths.
Ah, I see. Something like that works. You have to be a little bit careful about the order in which you process them rather than kind of breaking the ties all at once. But there are certain tie breaking methods that work similar to what you're saying.
Okay.
Good. Okay, so the moral here is just that this independence lemma is going to help us with the analysis. One point that I want to make is that even with this independence lemma in hand, there are still no good forbidden subgraph theorems for distance preservers, in the sense that, like, right here, all four of these color-coded paths are the unique shortest path between their endpoint, and yet, look, they make a C4. We're not going to say that it doesn't have cycles or anything like that. So, kind of hitting this with the same direct forbidden subgraph methods that we were doing before won't work. However, there is something very similar that will work, and the trick that I'm going to do is this. Instead, what I'm going to do is take an instance that we get of all these unique edge disjoint shortest paths and inspect its incidence graph. So what I mean by the incidence graph is this is a bipartite graph. The nodes on one side correspond to the list of demand pairs that we were given, or the paths if you like, since each demand pair is now uniquely associated to a path. The nodes on the other side correspond to the vertices of the graph. And the edges going between these correspond to membership. So for example, since the yellow path here has 4 nodes in it, those 4 nodes are the ones that would be placed adjacent to the yellow path in the incidence graph. Since this green path has 4 nodes in it, one of which is the same as one used by the yellow path, it would look something like this with one neighbor in common, and so on. Okay. Make sense, like what the incidence graph is of these things? So one thing to notice is that the incidence graph has essentially the same size as the original graph. In fact, the incidence graph is slightly larger. So it suffices to bound the size, not bounding the size of your distance preserver. And what we can do is kind of hit the incidence graph with forbidden subgraph methods like we were doing before. In particular, what the independence lemma is promising us is that the following 2 patterns are forbidden. This is saying that if you have like a blue path and a red path, they're not allowed to coincide on some intermediate subpath because the independence lemma is saying we can assume that they're edge disjoint. They won't coincide like this. And also, it's saying that if you have a blue path and a red path, they can't like split apart and then come back together later, like they're doing in this picture. This is because we get to assume that they have a unique shortest path, and unique shortest paths must kind of consistently choose the same subpath. Either this subpath between these nodes or this subpath between these nodes must be at least as short as the other, and then they would both take the short one. So those are both forbidden patterns in sort of the set of paths that we're inspecting here. And what that means, if you look at the incidence graph, is precisely that it does not have 4 cycles in it. You look at this incidence graph, a 4 cycle would mean that there's 2 paths, a red path and a blue path, that share 2 nodes. And if that were to happen, one of these 2 situations must happen as well. So what we get out of this now, I get to put my favorite 2 lemmas on the slide. Lemma 1 is the forbidden subgraph thing for distance preservers. It's that the incidence graph does not have any C4 subgraphs in it. And lemma 2 is we now get to hit it with this like high-powered theorem from extremal combinatorics, which is that the maximum possible number of edges in, now I'm in the bipartite setting, an NP node bipartite graph, that doesn't have C4s is this fairly complicated looking thing. Quick note on notation, it's sort of an abusive notation, but a common enough one that I'm going with it. If you have, we still write x for that same extremal function, but when you put 2 parameters like this, that means that you're talking about bipartite graphs that have those number of nodes on each side. Okay, good. So again, what I want to emphasize that I like about this method, and I'll keep showing you examples, is that we kind of get to offload all the hard work to extremal combinatorics. I will talk a bit, like in the later half of the talk, about how to prove stuff like this, but we just get to focus on like what structures there are or aren't in shortest paths. That to me has this more like TCS combinatorist flavor to it that's kind of fun. Yeah?
In the independence lemma, if you're assuming unique shortest paths, then wouldn't it make the problem very easy? You just compute all shortest paths and then add it to the...
Yes, so algorithmically, yes. Algorithmically, with the assumptions provided to you by the independence lemma, you have no choices to make. You just take the unique shortest path for each demand pair. What's still difficult is bounding the maximum possible size of the subgraph that could come from the union of those.
But they're edge disjoint, so...
Yes, they are. So all you're doing is like adding up the length of all of these shortest paths. But the idea is like maybe if the shortest paths are too long, they start to interfere with each other and they can't all be shortest in the way you might hope. Yeah?
What happens if the shortest path is not unique?
If the shortest path is not unique? So that could happen in the input instance. The independence lemma is sort of doing some magic in the background to reduce that instance to a different instance where it is unique. And then whatever distance preserver you build on that new instance implies one on the old instance of the same size. Yeah?
What is the significance of the plus n term? Isn't it dominated by n times square root?
Oh, good. So not quite. So you do need that plus n term to be sitting on the end there. The reason is that we're taking a min of these terms, n square root p and p squared and square root n times p. Yeah. Yeah.
So here you, so basically you folded C4 subgraphs. Suppose if you do find other structures potentially this bound could be improved further.
Yes, absolutely. That's a really good question. You're kind of seeing to something coming later in the talk, but that would be exactly the way to do it.
Okay.
Is there a hand over here? Everyone good?
So,
Oh, yes.
P is bounded by n, upper bounded by n for this bound to.
P is upper bounded by n squared here, since you can have at most n squared distinct demand pairs in your graph.
And this extremal property, this bound is still true.
Yeah, right. So that bound holds anywhere in the range p from 1 to n squared. Okay. Cool. Jump in if you have more questions. Otherwise, I want to point at something. I said undirected throughout this slide. I'm emphasizing that this slide only applies to undirected graphs. That's because the same proof does not work in the directed setting. Why is that? Does anyone spot the thing that was undirected specific in that last slide? So it's the C4s, yes, exactly. Specifically, this is the pattern that is allowed to happen among unique edge disjoint directed shortest paths that would result in C4s in your incidence graph, but it can totally happen. This isn't forbidden at all. You sort of have this blue unique shortest path going downstream and the red one hopping upstream like a salmon, and it can do that any number of times, and it's totally possible that those are both unique shortest paths in this graph. And if that were to happen, then we would get, in fact, many C4s. Every pair of these nodes that they have in common would be one C4 in the incidence graph. So it's no longer the case that C4s are forbidden. However, all hope is not lost. We just have to look for fancier forbidden patterns. And it turns out the one that will work in the directed setting is this right here. So I'm making the claim that if you have directed, unique, edge disjoint shortest paths, you will never have 3 different paths, a red one, a yellow one, and a blue one, that all hit the same pair of nodes. The reason being that 2 of those 3 paths would have to agree on the order in which they use the nodes, and then those paths would get you your contradiction to uniqueness or edge disjointness. And because of this, because of having this be the forbidden pattern in directed shortest path, K23s are forbidden in the incidence graph. When I say oriented, what I mean is that I'm only forbidding the kind of K23s that have 2 nodes on the vertex side and 3 nodes on the path side, but not the reverse. K23s with 3 nodes on the vertex side and 2 nodes on the path side are allowed here. To throw away those K23s. That's pretty much it. That's the entire proof. So lemma 1 is K23s with this orientation detail are forbidden in unique edge disjoint directed shortest paths. And lemma 2 is some high-powered theorem from extremal combinatorics that tells us exactly how many edges such a thing could have. It's not kind of strange looking down, but it's exactly the right answer. That's known to be tight. Okay.
At some point, we will run out of extremal combinatorics.
This is true. In fact, we're very close to that point right here. Extremal combinatorics is not as far along on figuring out these bounds as you might hope. They've been working on it since the 60s, but we've pretty much burned through the results in 20 minutes. Good. Okay, so I'll keep going. I'm going to do one more kind of similar thing. I'm going to talk about reachability preservers next. These are very similar to distance preservers, but even less constrained than distance preservers. Here, all you have to do is preserve reachability, as the name suggests, between each demand pair, rather than preserving distance. I was very lazy here and used exactly the same picture, because every distance preserver is also a reachability preserver. But you get the idea. There exists a path in H between the green demand pair, so it's valid. Okay, so the theorem that I'm going to prove for you, I wasn't sure how to cite this. Like, all those terms came from different papers, so I just called it folklore out of safety or something. This is the bound that is known, or at least was known for a while. I'll tell you about an improvement in a little bit.
Is that a typo? This is the distance preserver.
Oh, you're right, that is a typo. Apologies. I wrote that you have to preserve distance up top. That is a typo right there. That should just say that if there's a path from S to T in the input graph, there's also a path in the preserver. Okay, going back to this, like, how cheated do you feel question thing, It turns out that this is implying as a corollary that if you have slightly more than square root n demand pairs, you can go up to something that's roughly square root n log star n or somewhere around that. You can preserve all of those reachabilities using just ordered n edges. Another major open question that I think is very interesting is whether that threshold is tight. It's currently consistent with what we know that you could push that as far as n to the 2/3. Okay, so let me say a little bit about how you prove that bound. Once again, even though that bound looks horrible and I don't want to like read any of those terms, it's not horrible, or rather we can like blame the horribleness on the extremal combinatorics. We're just going to do some very simple like forbidden pattern thing. So once again, we get to have an independence lemma. Yeah?
So square root n distances can also be preserved using ordered n edges.
That's right. In undirected or DAGs, not in directed graphs.
Okay.
Or at least it's unknown in directed graphs.
Okay.
But this one, we're getting even more than that. We're like squeezing out just very slightly more pairs.
Right.
Good. Okay, so just like there was an independence lemma that like ruled out the need for tie breaking or anything like that for distance preservers, we have the same thing, fortunately, for reachability preservers. There's a lemma that says we can assume there's a unique path. There's only one path in the entire graph between each demand pair, so we just have to take that. And here's what that implies. First, that implies that C4s are forbidden in the incidence graph, and here's why. A C4 in the incidence graph would imply one of these three structures in the set of paths that you selected for your demand pairs. This one here is forbidden because we said they're unique paths, so they shouldn't be allowed to split apart and come back. That would imply two different paths. We also said that there's unique paths, and the way that that works is kind of the strong sense that there can't be directed cycles either, because then one of these paths could like take a few loops around that cycle if it wanted before going on its way. That would count as a non-unique path for purposes of this lemma. And similarly, we get to assume that they're edge disjoint, so they can't coincide. Together, those imply no C4s. But we get to keep going now. In addition to no C4s, it turns out we also don't have C6s in the incidence graph. And this is the picture that rules it out. You can't have a directed cycle worth of three paths for the same reason. You also can't have two paths that sort of form a bridge over this blue one down there, because that would be a non-unique path. That blue path has the alternate option of following the red and yellow paths instead if it wanted. So because of this, we have both no C4s and no C6s. Now, there's our forbidden structure lemma. It's very nice. We just say the incidence graph has no cycles of length less than or equal to 6. 3 and 5 are just ruled out because it's bipartite. And then, because of the way that the extremal combinatorics, or I guess the world works, that is the horrible bound that's what's known for bipartite graphs without anything less than C6. But all you really need to know is no C6s, and then like maybe you Google that bound and you need it or something. It's the way to approach this. Cool.
Sorry, one
Yo, yes.
one question. Why stop at C6 here? Why not go to C8 also?
Good question. C8s are possible. So it turns out that if you have a C8, one possible way you could get a C8 going on there is if you had like two paths that split apart from a common node, and then two other paths that came back together, and there would be no violation in that picture. However, there are certain configurations of four paths that are forbidden, and I'll get to that in a little bit.
C7 is also not allowed because of bipartite graph.
That's true. C7.
Some bounds or no?
It is not. So you're right that we could write C less than or equal to 7 throughout this slide instead of 6. It would imply the same bounds, but it would be equally correct.
I mean, is it even possible to ask about a complete characterization of this subgroup?
Sorry, say that again?
Like, is it possible to get a complete characterization of which subgroups are forbidden?
Sort of. So I'm going to give you a complete characterization of something that's forbidden in this, but it won't be subgraphs. We'll get to that in a little bit. Other questions so far? Cool. Okay, so here's where we're at so far. So in order to like completely solve one of these objects, in order to have provably tight bounds, you need a green check mark in both columns. You both need a structurally tight object that you can, like forbidden structure that you can reduce to, and you also need to know the correct extremal function for that particular object. The only one where we have that is single source distance preservers. For all of these other objects, there's a weakness on one side or both. So these are all the state-of-the-art bounds that I've shown you, with one exception, which I'll correct in a minute. But this is what is known, and that's telling you like where there are opportunities to potentially improve these bounds. Okay. So a quick note that I just want to say, some other objects that use similar methods for their state-of-the-art upper bounds, but which I won't talk about. Additive spanners for unweighted graphs are a major one. We talked about multiplicative spanners where there's like a times k gap in the errors that you're allowed to take on. You could also ask what if you get like a plus k gap in the error you're allowed to take on. Turns out there are three major upper bound results for this. You can have a +2 spanner on end of the 3/2 edges, a +4 spanner on roughly end of the 7/5 edges, a +6 spanner on roughly end of the 4/3 edges. Unfortunately, it turns out that the fun stops there. You cannot have like a +8 spanner on any sparser amount. But something cool that happened, there's this nice paper by mathematicians from 2014, which basically showed an alternate proof of all three of those bounds that did some fancy implicit incidence graph analysis, like what we're talking about. One other object is, we've been talking about distance preservers for weighted graphs. You can also totally talk about these things in the setting of unweighted graphs. Those tend to use these incidence graph methods as well. Okay. Good. So I'll keep going here. So the next thing that I want to talk about is moving beyond incidence graphs. So I'm going to now introduce yet another technique that will help us discuss forbidden patterns. When we go to an incidence graph, we lose information. If you're only focusing on the incidence graph that you get out of some system of paths that you selected, you are forgetting the order of the nodes along each path. And that's potentially lossy. So the next idea that we're going to have is, what if we don't forget that information? What if we treat that system of paths as a combinatorial object in its own right, and we talk about what patterns that directly does or does not have? So path system is this it's the name for the official combinatorial object that we're speaking of. Technically speaking, it's a sort of hypergraph, but I really like to imagine it as these vertices floating in space, just like any graph. And instead of edges, it has these longer paths passing through it. The only thing is that these are abstract paths. They don't need to be hosted by some implicit graph or anything like that. So here's an example of a path system. It has 6 nodes in it and 4 paths, which I've color-coded. Some terminology that will be relevant to us. We can speak about the size of a path system. We'd like to do that so that we can talk about what's the maximum possible size of a path system that avoids something. That's just the sum of the number of nodes in all the paths, which is equivalently the number of edges in the incidence graph. That's 2 ways to think of this size notion. That's why we're choosing that. Here there are 4 paths, each of 3 nodes, so we would say the size is 12. A subsystem, so if we're going to talk about forbidden structure, we need a notion of subsystems. A subsystem is any system that you can get to by starting with the original path, and then 0 or more times you delete paths from the entire system, or you delete nodes from the middle of some paths. So for example, that thing right here is a subsystem because you could take just A, D, and E, delete the other paths, delete the other nodes, and that's what you would wind up with. Good. These pictures are directed path systems. You could also totally talk about undirected path systems by just removing the arrowhead from the diagram. How would you get A to E? So you would just delete the node C. So the operation of deleting a node from the middle of a path and then it just sort of passes from one node to the next is something that's allowed in these subsystems. Yeah?
When you delete a node, are you removing it from all paths or just from one of them?
Let's say just from one of them if you like. Sure, yeah. There are some papers that use a more delicate notion of subsystem, but that simpler one will work for this talk. Okay, so speaking of these path systems, let's go back to reachability preservers now and see what we can do. So what the independence lemma was saying is that we get to assume that we have unique edge disjoint paths in our system, in our input instance that we're given. And another way to express that in the language of path systems is that this thing right here, which is a particular subsystem, which I'm calling a two-bridge, just has two paths that use the same pair of nodes, that is a forbidden subsystem in whatever system of paths you get from your reachability preserver. So is this three-bridge, because that would imply a non-uniqueness for this path that I've labeled the river. So is the four-bridge, because these arcs, these three arc paths combine to form a non-unique path, and so on. So there's now this like infinite list of forbidden subsystems. And with that in mind, we can now write down our forbidden structure lemma, which is that the system of unique edge disjoint shortest paths and end nodes graphs lacks bridges of any size as subsystems. And this might feel a little bit silly to you that we went through the trouble to write this down. Like, is this really expressing a new idea that we didn't already have? In order to convince you that the answer is yes, it turns out that you can prove a better extremal bound for these forbidden bridges than you can for forbidden C6s. So moving to this new forbidden pattern actually does do something. This improved some like long-standing bound on reachability preservers. Okay, so this is sort of trying to emphasize the importance of this view and of really nailing down the right forbidden pattern to work with. So you get that new bound. That is what is the current state of the art, and I'm not going to read it to you. It has too many square roots in it. Okay, yeah, the point being, though, that this is polynomially better than whatever we had before. Okay, so we have this structural upper bounds. The other thing that I want to point out is that we have a matching structural lower bound for these objects. The matching structural lower bound is that any path system that has no bridges in it in the first place implies that you just have to take all the edges in your unique path when constructing the reachability preserver in the first place. So for that reason, we know that the best possible bound that exists for reachability preservers is exactly that extremal function, NP, and then all forbidden bridges. Good. The asymptotic value is unknown. I'll mention that a little bit in the next talk if we have time, which I'm no longer so sure about, but it's open. It's an open question there. Okay, so here's where we are so far. I've now updated reachability preservers to say that if we use bridges as the right forbidden subsystem rather than 6 cycles, we now do have a structurally tight bound and an improved implied bound, but we don't know that that's the right extremal bound. In fact, I would conjecture that it's not, and we still need to do work on that. Okay, I have more to say about this, but I'm also at time for the first round of this talk, and this feels like a good breakpoint. So I'll wrap up there, take any final questions, and then pick up on this slide and show you what this path system bridge stuff does to distance preservers when we come back from the coffee break. Yes?
So you mentioned several impedance lemmas. I'm wondering, are these impedance lemmas also useful from an algorithmic perspective, i.e. are there algorithmic reductions from general instances to instances where the shortest paths become unique, or whatever you're trying to preserve becomes unique, and then you can retrieve what the actual preserver on the original graph from these unique paths on the...
Yeah, that's a very good question. The answer is mostly no, unfortunately, in the sense that these are extremal reductions. They're not so much saying that an algorithm for one setting implies an algorithm for the other. It's more like saying an extremal bound for one setting implies an extremal bound for the other, which is different. There are very simple greedy algorithms that don't require any of these extremal reductions, though. The simplest is what's called the decremental greedy algorithm. What it is you go edge by edge in the input graph, and if it's legal to delete that edge at the current moment, greedily you do so. This is not terribly fast because you kind of have to recompute things after every deletion if you're not smart, but it is terribly simple and it'll give you whatever optimal bounds you want. Thanks. Other questions?
Is there something you can say about into the 2 minus square root 2?
It's a bit complicated. It's coming from some recursion that solves to that being the root of some higher degree polynomial or something like that. I wouldn't focus too hard on trying to squeeze intuition out of that number. Other questions? Cool. Okay, I'll pick up here in half an hour then. Thanks.
We have a small token for you.
Oh, thank you.
Yeah. we'll continue at 11 after the break.
Very nice.
Yeah, very nice.
Okay. We good to go? All set? Awesome. Okay, hey everybody. Welcome back. So we left this talk on a thrilling cliffhanger, so let me go back a couple steps and remind you what we were doing. So we started by talking about like how far you can go by observing that your graphs that you're constructing have forbidden cycles. And then we extended that to say like how far can you go by saying that your incidence graphs to the path systems you're constructing have forbidden cycles. And what we did right before we finished was we now looked at these like types of cycles, these things that look like cycles in path systems that we called bridges. They have like two arcs, and then it looks like a directed cycle with one of the paths in that directed cycle reversed, which has this special name. It's called the river path. And we were sort of in the process of looking at how far you can go by observing that these are forbidden as subsystems of some path system. And the punchline that we left off on was that forbidden bridges of all sizes turn out to be exactly the correct forbidden pattern to associate to reachability preservers, and that doing so, in fact, provides you with this improved extremal bound down there at the bottom. Okay, so this was tight, and we ended last session on this right here, where we got to like put a green check mark in here. We moved one step closer to filling out this chart in the way that we wanted. What I want to look at next is these two conspicuous red X's going on right there. So we don't yet have structurally tight forbidden patterns for distance preservers either in the undirected weighted or in the directed weighted settings. So here's what we can say. What is true is that if we are in the setting of directed graphs, the 2 bridge is a forbidden pattern. This is coming from that independence lemma that we kept talking about. When you are constructing a directed distance preserver, you get to assume by that lemma that you have unique edge disjoint shortest paths. And what that means is that no 2 of your paths can share 2 nodes, because they either use the same subpath between those nodes, that's a violation of edge disjointness, or they use different subpaths between those nodes, that's a violation of uniqueness. Okay, so we get 1 out of those infinitely many bridges to be forbidden for directed distance preservers. So we can write down this new forbidden subsystem lemma that it doesn't have B2s in it. But it turns out that the associated extremal bound, this is something that we proved in the paper that introduced these, is that thing in purple. And that specific extremal bound for 2 bridges being forbidden, that turns out to be bad news. That is a no-go theorem. Because what it's saying, that purple bound is exactly the same extremal bound that we had previously when we were using K23s as our forbidden structure from the incidence graph. So it's saying that moving from K23s to B2s, even though that type of move helped us a lot for reachability preservers, it's just not going to help us for directed distance preservers. Similarly, we can look at the undirected setting. I was a little bit lazy and I didn't remove the arrowheads that we should have here, but like you can imagine that the undirected version of a 2 bridge is forbidden in an undirected path system that has unique edge disjoint shortest paths. And there's exactly the same no-go theorem that applies in this setting as well. Even though B2s are forbidden in undirected distance preservers in the same way, we can establish that the extremal function for those is exactly the same as what we got when we were using forbidden C4s in the incidence graph instead of forbidden 2 bridges. So this is entirely bad news. And to make matters worse, if we try to think, like, okay, besides that 2 bridge, either the directed or undirected version, are there any other forbidden subsystems in a system of unique edge disjoint shortest paths? That question, like, the natural thing to do is to look for more forbidden structures and try to exploit those. But that question turns out to be fairly difficult. It's not so obvious to come up with a new forbidden subsystem or even recognize if there are any. However, turns out the good news is that there are more forbidden subsystems than just a B2. And so that's what I'm going to talk about next. I'm going to show you what else is forbidden in unique edge disjoint shortest paths besides a 2 bridge. And here's the first one right here. I actually showed you this earlier as an example of a generic path system. It turns out it's a very special one. What's special about it is that this, in some formal sense, is the smallest path system that is forbidden as a subsystem of unique shortest paths, despite not containing B2 as a subsystem. So to quickly verify that it doesn't contain B2, if you look at any 2 of these 4 paths over the 6 nodes, they only intersect on exactly 1 node, so that tells you it doesn't have B2. And yet I'm about to prove for you that there's no way that you could possibly assign edge weights to these, how many? 8 edges going on in this system that would make all 4 of those colorful paths unique shortest paths at the same time between their endpoints. So here's how you prove it. I'm going to show you sort of a boring proof and then a cool proof in that order. Let's start with a boring proof. So suppose for contradiction that there were some way to assign weights to those 8 edges that resulted in all of them being unique shortest paths. We could use that to write down some inequalities. Here's the first inequality. what that is saying is that whatever weight we assign to AC plus CE, like the two parts of the red path, needs to be strictly shorter than the weights along this alternate path. This is just saying the red path is a unique shortest path. That's how you interpret that inequality. Second, we could write down another inequality, which is basically saying the yellow path is a unique shortest path by saying the sum of the two yellow weights needs to be strictly less than this alternate path between the same endpoints. Do the same for the blue path, do the same for the green path, and now notice that those cancel. Every term appears exactly once on the left and exactly once on the right. So if all four of those inequalities were true at the same time, we have 0 less than 0, there's your contradiction. Okay, so we have this like kind of algebraic proof, and we found, in addition to B2, there's whatever this thing is our next forbidden pattern that we get to add to the list. So, okay, so now what? Do we start like looking at those two patterns and trying to prove extreme Labounds on those? That doesn't seem all that fun, honestly. Like, what is this thing doing? And a better question, a better direction that I want to look in is where can we find more? How can we use whatever proof we just did to come up with additional forbidden patterns, additional forbidden substructures in a path system of unique edge disjoint shortest paths? And in order to do that, it's helpful to reimagine the proof that I just showed you with the following picture. Okay, so you have to stare at this one for a second to kind of put the pieces together and see what it's saying. But here we have a path system that has 4 colorful paths over 6 vertices. Here we have an octahedron, which is a shape that has 6 total vertices. In fact, they're labeled the same as the vertices over here. And I've 2 colored the faces. There's like a red face, a green face, a blue face, and a yellow face. And they're done in kind of this alternating checkerboard way so that no 2 colorful faces share an edge. So it's a proper 2 coloring if you view like gray versus colorful as the 2 colors. And the connection runs even a little bit deeper than that. If you look, for example, at the red path that goes ACE, and you look at this red face and you go clockwise around it, it goes ACE. So it matches. And the same will be true of all of the other colors. The green path is BDE, and those are the 3 edges on the green face, red in clockwise order. So this path system, in some important way, embeds into this octahedron. There's also this slightly technical endpoint edge condition, which is basically saying like between AC and E, those 3 edges are not all playing the same role as each other. 2 of them are like actual edges in the graph, AC and CE. The third one is kind of marking the endpoints. It's this AE edge. And there's a constraint that no gray face can have more than one of those endpoint edges on it. That's just there for technical reasons. But this path system that I drew embeds into a 2-colored octahedron in this particular way. And the general theorem that provides us with new forbidden structure is that any path system that embeds by these rules into some 2-colored polyhedron is a forbidden structure in a system of unique edge disjoint shortest paths. Including this, also including a lot more. There's a little note here, which is that you have to include degenerate and toroidal cases. By degenerate, I mean for certain really large polyhedra, it could be possible that like 2 of the nodes get identified with each other. Won't go into that too much. Toroidal polyhedra, I'll show you a picture of that in just a moment in case you haven't seen those before.
Intuitively, what is the reason that this clockwise thing?
That the clockwise thing works? So the importance of the clockwise thing is that, how do we put it? I'll try to give some intuition for why this is showing up. So in this proof that we did a moment ago, there was this kind of matching going on. We were saying that we were taking AC and CE, and then using the endpoint edge AE to match that onto this alternate path. We matched it to AD and DE. If you then go to this polyhedron picture, we have ACE is canceling against ADE, this adjacent gray face. So like the other inequalities correspond to the gray faces. And this technical constraint that you need 1 endpoint edge per gray face is giving you a perfect pairing between the 2 sides of the inequalities from before. It's a bit sorry, yeah?
Why is it called 2-colored?
2-colored, good. So generally, if I'm When I say two coloring, I'm treating the colors as gray versus colorful. And it's sort of in a checkerboard pattern, no two colorful faces share an edge, no two gray faces share an edge. I'm just distinguishing among the colorful faces for the sake of showing the mapping to these paths. Yeah?
One small question. So this is the 4 lines, and every point has 2 lines. There are 3 points. This reminds me of this the projective plane. Is it something projected to that?
Yeah, good. It has something in common with the projective plane. The thing that makes it not a projective plane is that the projective plane has that property and it has the same number of nodes and paths, whereas this has more nodes than it does paths. But if you were to kind of do a version of this construction that was balanced, you'd be exactly right. It would be a projective plane. Okay. Cool. So,
For any path system, you will get this clockwise order of the polyhedron.
right. So it has to like respect the orientation of the polyhedron in order to be forbidden, according to this. Let me show you a couple more examples of this theorem in action. One of my favorite applications of this theorem is that you get like colorful pictures in talks, so I want to take advantage of that when I can. Here are some more path systems that are forbidden as subsystems in any system of unique edge disjoint shortest paths. You will never find this thing right here. Kind of has, it's a little tough to see the colors here, but it has sort of these paths that are looping around in some predictable order. The reason why is that this embeds by the same rules into this 2-colored hexagonal bipyramid. That's what tells you that it's a forbidden substructure in unique edge disjoint shortest paths. Here's another example. You can kind of see how these are fitting together into, this is an elongated square bipyramid. I had to learn all these to write this paper. That one on the right, that is an example of a toroidal polyhedra. So we have like, it's bigger. We have 16 nodes going on and about 8 paths going on in that picture up there. It will embed into this structure right here. If you haven't seen this diagram before, this is called the fundamental polyhedron of a torus. It's sort of like saying, imagine taking these 2 arrows and like gluing those sides together, wrapping it around. And then imagine taking these double arrows and similarly gluing those sides together and wrapping it around. And if you do that, if you can kind of do that bending and gluing in your mind, you'll see that the shape has become a torus. And so this is a representation of like a polyhedron where if you were holding it in your hands, it would have a hole in the middle as opposed to being a normal solid polyhedron. And those are allowed. Like embedding into that sort of polyhedron also makes it a forbidden subsystem. Yeah.
Proof that these subsystems, these structures cannot be present. Is it similar to the one where we took inequalities and then summed up the inequalities, like the previous one?
Yes, it is fairly similar to that. There's a few extra details going on, but the core of the proof is that, and then you have to kind of dispatch with some new corner cases that arise, I would say.
Is there any other way to look at this, like some kind of generative case, like using some expansion and like edge expansions, looking at it as polygons?
So are you saying like some other way to describe this list of forbidden patterns besides through the lens of polyhedra?
Like graph minus instead of polyhedra.
That is a good question. If I had to speculate, I would say yes, there's some other way, but I don't know it. I haven't seen anyone like come up with that, but it seems very possible.
Okay.
So if this is more than 3 sides, where are these paths where the side is equal?
So this one, for example, has a few paths with 4 nodes, so we could try to focus on that one. It works a little bit similarly in that you can imagine sort of rerouting each of these paths to some alternate path between the same endpoints. So this is a red path that just goes straight up the left side, BDGI. And the corresponding inequality on the other side would be what you get from going B to E to H to I. That would give you one of the inequalities in the system that you write down.
A nice little question. So, is there any deeper reason why polyhedrons are popping up when you're trying to analyze the forbidden subgroups?
Yeah. So it has to do with those systems of inequalities that we were doing before. Those systems of inequalities sort of have this flavor to them that there's cancellations happening. Like you have these left-hand side paths that are canceling perfectly against the right-hand side paths. And when you visualize this polyhedra, what you get is that you need like a set of colorful faces whose boundaries exactly cancel against the boundaries of a different set of gray faces. So it's about boundary cancellation.
Some form of greens, something happening, greens theorem kind of thing.
Oh, possibly. I'm not sure about that, but could be.
If you're talking about things cancelling on the boundaries that two faces share, it feels like some form of things flowing on the surfaces that are cancelling along the boundaries.
So it's possible. So you, in the formal proof of this, you really do invoke a boundary operator. It's kind of very similar to the one used in simplicial homology.
Mm-hmm.
It's defined almost identically. I don't know if I can comment on if Green's theorem is directly applicable here, but it is using these like boundary ideas for sure. Other questions here? Cool. Okay, so those are just like some more of the infinitely many path systems that get forbidden in a system by this theorem. One comment that I want to make is that these are all forbidden directed systems that I've drawn. They have arrowheads on them. And you could ask, like, what about undirected systems? Like, so if we're talking now about undirected distance preservers and we want to figure out what patterns are forbidden in a system of undirected unique edge-disjoint shortest paths, basically the same characterization works, but now we have to revisit this clockwise detail. One of the details was that, like, the red path is going ACE, and that specifically occurs clockwise around the red face. And if we're now talking about undirected paths, you can still require that ACE occur in order around the face, but it doesn't make sense to talk about it being in a clockwise or anti-clockwise order. So that requirement basically has to get removed in the characterization for undirected distance preservers or undirected path systems. Besides that, it's the same. But there's a somewhat interesting consequence of removing that orientation requirement, which is that now you get non-orientable polyhedra being forbidden as well. So this is a particular path system. You can kind of look at it. There's 12 nodes and 6 paths going on in this. If you were to that embeds into this polyhedron with these arrows again indicating some sort of gluing process. This one's a little bit tough to imagine, but try to imagine those double arrows getting glued together. So you're wrapping it around. This node is identified with that node. This node is identified with that node. And because these top and bottom arrows are in opposite directions, you have to identify those with a twist in order to get that. So it's a little bit mind-bending. You would have to pass through itself because that's how non-orientable surfaces work. But you kind of ignore that. You pretend like it doesn't, even though it would in 3D space. And topologically speaking, that is the topology of a Klein bottle there. So even this is exactly the sort of thing that becomes forbidden in the undirected setting that was not previously forbidden in the directed setting. That makes this path system and ones like it particularly interesting. They have the property that it's impossible to realize them as undirected unique shortest paths. But if you choose any orientation at all of those paths, it is possible to realize that as directed shortest paths. So they exactly capture the difference between the settings if they embed in a Klein bottle or similarly non-orientable surface.
Do you prove that this is not realizable via any way? It's again case analysis.
It's a fairly long proof. There's definitely some of that.
It's not. So it does require a separate proof. It's saying that if you believe that, if you take that as a proven fact that this is not realizable, what you get is it in any such embedding you won't have this as a say a homomorphism.
Yeah. So what you get is this will never appear as a subsystem of any set of unique edge-disjoint shortest paths.
Right.
And the way that you can prove that fact is just by exhibiting that a homomorphism into this Klein bottle, basically. It has to be a locally injective homomorphism, it turns out, but that's details. Yeah. Other questions here? Cool. Okay, so the upshot of all of this is basically this. This is the summary slide. If we I'm going to write Q sub und for the set of undirected path systems that embed into polyhedra, including this toroidal case, including this non-orientable case, and so on. And then Q sub dir for the directed ones with their set of restrictions. What we're basically saying, what we've proved through all of this, is that every undirected graph has a p-distance preserver of whatever the extremal function is of this. You have to forbid both that two-bridge, that's like an exceptional one that doesn't have a polyhedral embedding, but is forbidden nonetheless, and all of these undirected ones. And a very similar statement holds in the directed setting. That's what we just proved. And in addition to these being forbidden, it turns out you can prove that that's the complete list, that that's everything that's forbidden. So there it is, B2 union this thing and B2 union this thing. Those are structurally tight. So that's cool, that's good news. The bad news is nobody has any idea how to actually use that to improve the associated extremal bounds. It seems, if I had to guess, I would say that it is possible, but like ideas are needed. It's not clear which of these many, many subsystems out there we should be focusing on in our proofs or how this would even go, really. So those bounds that I've written over there have not changed from whatever they were before, but I would informally conjecture that maybe it's possible to change them. Anyway, that's where the intention belongs right now. Okay, good. So the structural side, like, it's complete. We got green, we got green check marks everywhere. These are all structurally tight. And on the extremal side, it's a disaster. We know what's going on with single source shortest path trees. Everything else needs a lot of work.
But do you think that we can get still linear bar when P is more than root n using this more forbidden structure?
Yes, so we do know that you can recover the existing results using this list of forbidden patterns.
But like, the question is, do you think that right now you get linear bar when P is root n?
Yes.
Do you think you can improve this?
Oh, I see. Using these new forbidden structures. Okay, I'm speculating hard right now. I would guess it's probably not possible for reachability preservers, that what we have is likely to be tight. And I would guess that it probably is possible for directed distance preservers. But I'm guessing. I'm kind of taking a shot in the dark here. Other questions? Okay, sweet. One other last little comment is kind of an interesting subplot in all of this has been Gabor Tardosh in 2018 wrote this survey about extremal problems in ordered matrices. So this is sort of like, you have a matrix, imagine all the entries are either zeros or ones, and I tell you certain forbidden submatrices that could show up in this. How many ones could it possibly have subject to those constraints? He's been looking at a lot of these questions, and it turns out that some function that is very useful in this can be shown to be equivalent to the extremal function of path systems that forbid a set that I'm calling beta. Beta is the set of all path systems in which every single path is a river. So for example, there's 4 paths in this system, and for any path you point at, say the red one, you can find some bridge that uses the red path as its river. Here, this like ADE bridge would be the example. So that is like, if you forbid all such structures of that form, he showed these bounds, it's sort of sandwiched between these two terms, and he conjectured that the lower bound is tight. There is some reason in this ordered matrix theory that I won't get into that you want to know that. It turns out we were able to prove that if you avoid everything in this system, that implies that it is definitely possible to realize the corresponding path system as unique shortest paths. So a consequence of that is that that extremal function gives you a lower bound for distance preservers, and there's some speculation that that could maybe be an upper bound as well. So that requires some work, but that would give us something much simpler and with connections to ordered matrix theory to work with in terms of figuring out what the right extremal bound is for distance preservers. Okay, just wanted to mention that quickly. This is a good open problem of whether you can reduce distance preserver upper bounds to this extremal function as well. A couple other quick notes. So again, I'm doing this like, here are some other places where forbidden patterns and path systems show up, especially recently. There's been this interesting direction of doing this to shortcut sets. So if you haven't seen shortcut sets before, the basic idea is you're given some graph. Here I'm focusing on directed graphs. And you want to add a small number of additional edges. So here I've added some red edges to the graph. and you're trying to make the diameter of the graph as small as possible. In other words, for any pair of nodes that can reach each other, you want the maximum shortest path distance to be small. Those red edges specifically, like the farthest pair is the two nodes at these corners, and with the addition of the red edges, the distance becomes 5, so it's a diameter 5 shortcut set. It turns out that like there's this recent line of work that I'm pretty excited about that basically recover/improve all of the existing shortcut set bounds by reduction to some like more complicated forbidden patterns in path systems. So this seems like a way forward on this problem as well. The other one that I'll mention quickly is the directed flow cut gap. So what that means is that there's this famous theorem that says min cut equals max flow if you're dealing with a single demand pair in your graph. But if you're dealing with an arbitrary set of demand pairs, not just one, these two quantities can in fact be very different from each other. The flow cut gap is trying to bound the maximum amount that they could be different from each other. So this, in directed graphs specifically, this is a significant open problem. There's very large polynomial gaps between the upper and lower bounds. But there's this recent direction. Chizoli and Khanna sort of started it in 2007 with some lower bounds. I have a forthcoming paper with my student Luba. This is Timothy Chan's notation. He says it's good luck to like cite your papers to the next year and it'll get them accepted. So forthcoming paper that's sort of doing reductions on the upper bound side as well. Okay, one last note that I have about these things before I move on to my second slide deck, we'll see how far we get into that, is I want to mention incompressibility theorems. So out of all of the graph sparsifiers that I've mentioned so far, another use of this is that they all have associated incompressibility theorems. So here's what I mean. I've been talking about subgraphs and like how many edges do you need in a subgraph, and sometimes people are like, who cares about subgraphs? We're computer scientists, we should care about data structures. For example, what an incompressibility theorem says is like, let's consider some data structure that performs whatever task the subgraph performed. Maybe it's like much more flexible though. So like if we're talking about single source distance preservers, this would be a data structure where you query it with a node and it tells you the shortest path from S to that node, because that's what a single source distance preserver could do. Or spanners, maybe you query it with a pair of nodes, it tells you an approximation to that distance, something like that. So anytime you have a data structure that does whatever the task is that is being performed by these sparsifiers we're talking about, an incompressibility theorem is something that says you can't, even with like the entire arsenal of data structure tricks available to you, you still can't use those to improve on the size error trade-offs that you're getting from sparsifiers.
This is for exact, right?
This is for every object that I've talked about so far. There's a theorem of this form. Yeah, almost every object in the area, with a couple notable exceptions, have this. Good. Here's just like a quick example of what I mean by a data structure that does the same task. If I give you a graph G and some stretch K, and you wanted a data structure that reports a times K approximate shortest path distance, or maybe even a times K approximate shortest path, this is like the data structure version of a K-spanner. This is sort of like what Google Maps is doing, or maybe it's like what Apple Maps is doing because it has this error attached to it. But it's if you were to like give it this input graph and you say I'm willing to accept ×3 error, it's going to pre-process that into some small data structure where if you query between two locations, this is like near where I live in California, it will give you some horrible path, but only ×3 horrible, not too far out there. And you could do that for arbitrary pairs here. So this is the data structure version of a spanner. And this incompressibility theorem was first proved by Matuszek in '97, and then sort of other versions of it have been proved since. It says that the space optimal data distance oracles, like the very best you can do in terms of the trade-off between the error k and the number of bits that you use, is achieved from a spanner. If you were to just build a sparse spanner and write that down, that gives you enough information that if I query 2 points, you could just compute the distance on the spanner, and that's a good approximation to the true distance. So all of this terrain, extremal, excluded stuff, it's not just about sparsifiers and subgraphs. These are also the information theoretic bounds for how good data structures can be that approximate these quantities. Okay, so that's the point that I wanted to make. Some common way to, here's like, you just, oh, sorry, yes?
So in terms of incompressibility, are there like ways to relate it with streaming lower bounds also, as in like some kind of distributed simulation of something?
For streaming lower bounds, interesting. Honestly, I don't know enough about streaming lower bounds to say, but it's a fairly flexible technique, so it wouldn't surprise me if something like that were possible.
So for constructing this sparse-spread graph, right, you still follow the greedy kind of algorithm which you mentioned in the videos, and if so, between all these forbidden paths, right, how do you choose the priority order of them? So first you do this kind of forbidden path and so on. So which priority should we take?
Yeah, so you're talking about specifically constructing preservers, like whether you're doing a greedy algorithm along these lines. Yeah, so the first part is actually not quite right. So you're doing a greedy algorithm, but it's not the same greedy algorithm as the spanner one. There are several that work. Maybe the simplest one is a decremental greedy algorithm. So what you do is you start with the entire input graph as your preserver. You go edge by edge, and then you check to see if it's currently legal to delete that edge. And if so, you do it in a greedy function. Okay, so just quick summary in case you missed absolutely everything that I said. Here's kind of what I just was talking about. So like simple greedy algorithms that are easy to prove correct. That's sort of the joy of this blue forbidden structure method as opposed to the red clustering method that I mentioned at the beginning. You observe some forbidden pattern, and then you do extremal combinatorics, or more likely like Google extremal combinatorics and use whatever bound you find. And that will bound the maximum possible size of whatever sparsifier you built. Okay, so I wrote to be continued after the break because I very ambitiously thought I might get here before the break. Anyways, I'm going to switch slide decks to the other one. You don't get a break this time. Okay, brief pause. Okay, good. Yeah, so I asked my cousin's 4-year-old what I should use as a picture for this talk, and he roared at me. So I interpreted it this way, so I don't know. Yeah, this is Paul Turan. He's the person who invented all of these extremal combinatorics problems. So here's what we're talking about, Turan-type problems. You've just seen an entire talk where these were showing up in the background. This is like the problem of getting one of these functions we were calling x, and then trying to figure out what bounds apply to it. That's a Turan-type problem. Here's the notation we were just using, which we will continue to use. The maximum possible size, for example, the maximum possible number of edges in a graph is a very common size notion that avoids some sort of forbidden pattern. For example, maybe C3 and C4, that's what you write to the right of the bar. And then this function is just measuring that. So for example, the most edges in a 10-node graph that does not have 3 or 4 cycles is 15. That is realized by the Peterson graph, which is like this famous counterexample graph that does lots of things. So that's how you would write that. Okay. Just some applications in TCS. First of all, I just gave you a whole talk about this, so I'm not going to say that much more about it. But some other ones that I didn't mention in the previous one. One really popular application of these theorems is subgraph detection algorithms. For example, if I give you a graph and now I want you to tell me, does this graph have a cycle in it of length 4 or less, or are all the cycles length 5 or more, it's kind of helpful to know that if the graph is sufficiently dense, you can just instantly answer, yes, it has a cycle, and you don't have to keep looking. So that's one of the other applications of these things. They show up in property testing a lot, a bit more indirectly. Just knowing the bounds on EX is not so useful in property testing, but many of the methods, especially regularity limit-based methods that are used to prove bounds, are what show up in property testing. Minor freeness as well. There's a question in the very beginning about, like, do minor free bounds count? And maybe it depends on who you ask, but I say yes, that is a type of Turan-type problem. So it shows up there as well. Many more examples, I won't still go into it. Okay, so I'm going to start by talking about Turan's theorem, which is the historically first one, and I'm going to do it in sort of a different way. Okay, so here's a puzzle. So you have 6 batteries, and you know that exactly 3 of your 6 batteries have charge, but you can't remember which they are. And they're all identical to each other. You have a flashlight that you would like to turn on, and you have to supply it with 2 charged batteries for it to turn on. If either one or both of the batteries are uncharged, it does nothing. So the question is, how many attempts do you need in order to guarantee that your flashlight turns on? Okay, start thinking about this. I'm going to say some stuff to clarify the problem and also like stall to give you a chance to think. But one thing that I'll say is that your strategy does matter, interestingly. Like, trying batteries in a certain fashion will realize a lower number of attempts to guarantee that the flashlight turns on than trying them randomly. To give you a couple examples, here's a way that you might go about representing a strategy. You're trying 8 different battery pairs, which I've drawn as edges here. So you could ask, like, is this a good strategy? Does it work? The answer to that question is no. This is not a good strategy for the problem, because it's possible that these were the 3 charged batteries and I never tried any pair among them. So this fails. Another strategy, here's like a different way that you can make 8 attempts. It turns out that this strategy does work. This is a correct strategy because for any 3 batteries that you pick, for example, these 3, you'll see that there's an edge going between 2 of them. So we did try one of the pairs.
Is it something like AB, AC, AD, AE, and then go from DC?
Not quite. I'll show you the example in a second. Let me do a quick straw poll. So I've just revealed that 8 works. Does anybody think that they have a solution using 7 attempts so far? By like show of hands? One person so far. Do you have 6? You have 5. I don't think you have 5, but you might have 6. Okay, good. So this is like a puzzle that you could like try to figure out. It turns out the answer is 6. The optimal solution is 6, and it looks like this. So if you were to try, like, break your batteries into 2 balanced groups and try all pairs within each group, you can now be certain that 2 out of your 3 charged batteries lie in the same group, and then you tried those. This is provably optimal. This is the best that you can do for the problem. Okay, we can generalize this problem fairly easily. So now instead of 6 batteries among which 3 are charged, I'm saying you have n batteries among which r are charged, but you can't remember what's what. So how many attempts do you need to guarantee that the flashlight turns on? What Turan's theorem says, in this like kind of alternate, this is definitely not how he originally wrote it, but this is a nice way to think of it, is that the optimal strategy for any n and r is always to split your batteries as balancedly as possible into r-1 groups, and then try all pairs within each group. That's how you should do this. It achieves the best bound every time. So for this particular one, we have 10 batteries. We are promised that 4 of them are charged. So the best thing you can do is split into 3 balanced groups and try all pairs within each group. That gives you a bound of 12 attempts. Okay, so I called this Turan's theorem. Now let me tell you what Turan's theorem like actually is. If you like tell someone this is Turan's theorem, they'll think you're crazy, so don't do that. But what it's really asking here, in like graph theoretic terms, is it's saying what's the sparsest possible graph that you can design that doesn't have an independent set of size r? Because an independent set of size r could be the charged batteries, and so you'd better have tried one. And if we just sort of take that problem and complement the entire thing, then what it's saying is what is the densest n-node graph you could possibly come up with that has no r-clique as a subgraph, just complementing the entire problem. And the complement of this is biclique. Biclique is bipartite, therefore has no triangle in it. It's as dense as you can do. Okay, good. A bit more generally, what Turan's theorem is saying is that this is not specific to triangles. The very densest n-node graph that avoids r-cliques is a subgraph, and now you can see how we get to this x of n. Well, that should say kr instead of cr, apologies. That should be the forbidden clique right there. Is this graph right here, which you get exactly by this split into nodes process I described and then complement. And in fact, there's this like vast generalization of Turan's theorem, which is called the Erdős-Stone theorem. It came out not too long afterwards. What the Erdős-Stone theorem says is that it's not just the r-clique. In fact, if you have any graph at all whose chromatic number is r, then the Turan graph with parameter r is the very densest n-node graph that avoids h as a subgraph, up to this this like hidden little o of 1 term right there, which could potentially be improved. So this gives us extremely sharp bounds for the problem. It's telling us like not just what the bound is, but what the leading constant is as well, which is more than we typically ask for, unless r equals 2. Because if r equals 2, then this term right here, that 1 minus 1 over r minus 1, just cancels out. And so that little o of 1 factor is the whole thing. It's what determines the function. So saying we have the right answer up to the little o of 1 function is not so useful. Okay, so what this is really saying is like, if you want to know about the excluded Turan function of any non-bipartite graph, we have a great answer for you. If you want to know about bipartite graphs, we are in deep trouble. We can't use this Erdo-Stone theorem, and our knowledge is very limited. So when it's non-bipartite, we know that the extremal function is theta n squared. We know the right leading constant. We know how many copies of h there are. We know some very deep structure of what the copies must look like, in fact. But we're going to be focusing on the setting where h is bipartite. Because we are theoretical computer scientists and we don't care so much about constants, this is sort of the more interesting setting, more applicable setting for many of these problems. Okay, good. So I'm going to show you how to prove some stuff. There is like one sort of glimmer of hope in all of this, which is that one type of graph where we do know the Turan function, even though it's a bipartite smaller graph, is a path. If I were to give you any constant fixed length path, then if you are excluding that, if you're saying this is a graph that has no 3 paths in it, that immediately limits the number of edges in the graph to theta n. And in fact, we can say a bit more than that. If you surpass that threshold, if you have more than the extremal function number of edges in your graph, not only is it the case that you definitely have a path pi, we have bounds on the number of paths pi that you must have. It's this like n times omega d to the number of vertices minus 1. Quick proof sketch of this, if we look at like a 3-node path pi, you get to choose a node for g. There's n options for how to do that. There's theta d options. I'm just going to assume it's a regular graph for simplicity for how to extend that by an edge. And then you do that one more time in order to get a copy of pi. Counting the number of ways to build that leads to that counting bound. So with this path counting lemma in our pockets, we are now ready to prove the first of these many extremal functions that I claimed in the first part of the talk, which is the extremal function of an n-node graph with a forbidden C4. At some point I said that that was n to the 3 over 2. Here's how you show that. What you do is you kind of factor your C4 into 2 different 2 paths that share endpoints with each other. There's a solid red one and a blue dotted one right there. So from that diagram, we can see that if your graph has no C4s, then it's not allowed to have 2 distinct 2 paths with the same pair of endpoints. That leads to this inequality right here. Here's the lower bound on the number of 2 paths in our graph. Here's the upper bound. It's at most n squared by pigeonhole because we know they can't share endpoints with each other. And just kind of putting that together, comparing that first term to that last term right here, we get that d is at most square root n, and if your graph has average degree at most square root n, then it certainly has at most n to the 3 halves edges overall going on in it. Okay, that's the first one. The more bound is the name for this general term. So it's proved in exactly the same way. All you do is you kind of take your 2k cycle and you factor it into 2 different k paths. So here k equals 3. If you have 2 different 3 paths that share endpoints, they either look like they do on the left or like they do on the right. In either case, they imply a short cycle of some kind. We get this inequality, and kind of by the same calculations, we get our desired bounds. Okay, so this is called the more bound. It's like this very simple, clean counting argument. And it's reasonable now to ask if it's tight. So the first bound, if we like plug it in for C3s, it's telling us that if you forbid triangles, the extremal bound is at most order n squared. Turan's theorem is telling us that that is the correct bound from a biclique. If we plug in forbidden C4s or C5s, it's telling us that the bound is at most n to the 3 halves. That too is known to be tight. So more good news. If we plug in forbidden C6s or C7s, they're sort of like slightly fancier group theoretic constructions that tell us that once again the more bound is tight. For the next one, we don't know. We actually like stopped being sure whether or not the more bound is tight for C8s and C9s. The best upper bound is n to the 5 over 4. There's no matching lower bound that is known currently. Fortunately, then after that, things return to normalcy. We do know the correct bound for forbidden C10s or C11s. And then after that, chaos reigns again, and we have no idea what's going on. We don't have any tight bounds beyond that point. Okay, so this is called, the girth conjecture is the conjecture that, in fact, the answer is yes for every row of this table, that the more bounds are always tight. this is an extremely difficult problem. Like if you solve it even for one specific choice of k, you become famous in the right communities. So, take it with a grain of salt. It's also controversial in a way that I find very interesting, in that a lot of TCS people will write papers that depend on the girth conjecture, and they'll write stuff like, this is obviously true, this is uncontroversial. And there's been a recent trend in extremal combinatorics where they write papers that depend on the girth conjecture or talk about it in some way, and they write, this is obviously false, there's no way that this is true. And somehow the communities are not talking to each other, we're drifting off in different directions. So the best I can say is that it's controversial. Depends who you ask on whether or not this is actually likely to be true. Okay, I'll say, I got about 10 minutes, so I can say a little bit more. So I talked not just about the forbidden patterns of cycles, I also talked about forbidden patterns of bicliques. I'll say a little bit about how you extend arguments to get there. So in an extension of the path counting argument that we talked about before, basically the same thing holds not just for paths, but for any fixed tree. Which is to say, if you forbid any fixed tree, the extremal bound is theta n. And in fact, if you exceed that extremal bound significantly, we have very sharp bounds on the number of such trees that must exist. So the proof, I'm going to skip this, but it's basically exactly the same. You just choose a node and then grow your tree step by step, count the number of options for how to do so. This will give you some sort of tree counting lemma. And by far the most widespread and successful method for proving Tarrant-type bounds for bipartite graphs is what I'm going to call tree splitting. So it's this three-step process, and I'll show you an example of it as we go. You find some way to partition the forbidden subgraph H into symmetric trees. So for example, let's say that we're trying to figure out the extremal function of forbidden K23s. Here's a K23, and a way that we could split that into two symmetric trees is like this. There's a red tree right here, which is a claw, a K13, and separately a blue dotted tree right there, which is also a claw, a K13. Then the second step is to say, by the pigeonhole principle, we can limit the number of copies of this tree that can exist in an H-free graph, because if there were n cubed of these overall, we would be able to say that two of them must collide on a node triple, and in doing so form one of these K23s. So putting that together, it leads to this bound. We have a lower bound, we have a tree counting lemma that tells us how many of these there must be, and an upper bound on the number of these that there could be. Putting that together implies that the extremal function of forbidden K23s is n to the 5/3. Okay, there's sort of a problem with this, though. So the problem, when I say there's a problem, I don't mean that it's incorrect. It is true that the extremal function is upper bounded by n to the 5/3 for exactly this reason. But there's this pitfall that shows up in these arguments, where the way that you factor a graph into trees is very often non-unique. And for this particular one, there's a separate way to factor it into trees, which looks like this. Now we are splitting it into three separate two paths, which all collide on two nodes. And in doing so, we can then run through the same motions. This tells us that there can only be order n squared two paths in the graph, or else they would have to collide in the wrong way to form a forbidden K23. And if we run through the steps of using that tree factoring instead, it will lead to a better extremal bound. It'll lead to n to the 3/2. So sometimes to get the right bound, you can't just use the first tree factoring you spot. You have to be a little bit more careful. Good. So that's the right extremal bound. That one's tight on the right. Okay. You now mostly know the techniques that are used. There's sort of one very important one called the Ruta-Zimmeretti theorem, which I've not talked about, but this is the main one. There's a bipartite extension of this. How much can I say about this? I'm going to go a little bit quick through this. I'll sketch this just so that I can very briefly point at the last step. So if we wanted now to do the bipartite version of this problem, let me point at what changes. If you want to know the extremal function of a bipartite graph with n nodes on one side, p nodes on the other side, and forbidden C4s, we can again use this strategy of counting two paths, but we kind of get these two different inequalities coming from the two different ways to factor a C4 into two paths. So here's what I mean. one observation is that the number of two paths that have both of their endpoints in the v side is bounded. It's at most n squared, because otherwise we'll get like a red path colliding with a blue path, like this. And similarly, the number of two paths with both endpoints on the other side is at most p squared, because otherwise we'll get a collision on the other side. And so a little bit similar to the K2-3 that we just saw, these are going to lead to these two separate bounds from each other, np to the 1/2 plus p, and also n to the 1/2 p plus n, if you work out the algebra. But what's tricky about this is that before we were like, yeah, there's two different ways to factor out this subgraph, and one of them is better than the other. In this new setting, these two different ways, which one is better depends on the relative sizes of n and p. So you can't just say that one is better than the other. You have to carry these both around. And if you remember in the first half of the talk, when we looked at this extremal function and had this like complicated min of two terms going on, getting mins in that way is very common in this area for exactly that reason. There's often two different ways to do tree factoring, and then you have to take the min of the two bounds that you receive. Good. Okay, for C6, I'm going to point something out here. So interestingly, C6 works differently than C4. For C6, we want to do a counting argument based on 3 paths instead of 2 paths. And since 3 paths have odd length, they're going to start and end on different sides of your bipartite graph. And a consequence of that is that you only actually get one inequality out of this. You get that the number of 3 paths overall is bounded by n times p, since that's like the number of pairs of endpoints that can be used. So for the bounds that you get for forbidding odd cycles tend to look a lot simpler. They don't have the same min term showing up as for even cycles. So this is what you get for 3 paths. Now let me do this. This is, I think, where I'm going to wrap up the talk after I make this point. So just like we asked whether the Moore bounds were tight and uncovered this major open question, you could ask whether the bipartite Moore bounds are tight, these bipartite more expressive ones that we just came up with. So the first one is, if you forbid C4s, you get the min of these two terms, and that turns out to be fully tight. Every single point on this trade-off curve, no matter what n and p are, can be realized by a matching lower bounds. The next one is pretty interesting. The next one is this bound that we just came up with for forbidden C6s is known to be tight for some values of n and p, and also known to not be tight for other values of n and p. There's this different argument that improves on this, which is surprising and rare. The amount that it improves on this is tiny. It's by like roughly log star factors of use of the log star in the wild. A similar thing happens for k equals, so k equals 4 is just totally open. We have no idea what's going on if you're forbidding C8s. If you forbid C10s, a similar thing happens. It's known to be tight for some values, not tight for other values, and it's kind of unclear what's going on there. At that point, we just know what's going on even less. We have no idea what's going on for C12s or beyond. For forbidden C14s, we know this to be tight for some values of n and p. It's conjectured to not be tight for other ones, just like 3 and 5 weren't. But this is kind of an open problem on the forefront right now. Good. This is called the bipartite girth problem. To give citations for these last two things that I said, the improvement on the bipartite Moore bounds for forbidden C6s came from this paper by Decon and Zekeli in 1997. They proved it by reduction to the Rouget-Zemiretti theorem, which I won't have time to talk about, so ignore that covered next bit. But that's the relevant toolkit if you have heard of that before. This improvement for forbidden C10s is very recent. It was by Conlon, Fox, Tudikov, and Zhao in 2021. And they just sort of like figured out this sparse version of the Rouget-Zemiretti theorem that's enough to push it through. So these are considered, I mentioned earlier that combinatorists generally disbelieve the girth conjecture. This is one of the major reasons why they disbelieve the girth conjecture. We know that the Moore bounds are not the right thing in the bipartite setting, so it's kind of like, why should they be the right thing in the non-bipartite setting? Good. Improving the Moore bounds for any odd k greater than or equal to 7, kind of continuing this trend that we've seen, I think is a very good open problem. Okay, so with that, there's this whole Rouget-Zemiretti theorem thing, which I'm going to skip for the sake of time. And here's a quick conclusion. Here's my my open problem list. So the goal, some of the many open questions that I've discussed throughout the talks, improve the extremal bounds for preservers of any kind, especially this linear size threshold. Figuring out the number of pairs that you can support with order on edges is good. This question I just mentioned about improving the Moore bounds for bipartite C2Ks when k is odd. finding forbidden structure, like making this method work on other new objects, just like expanding the horizons, is a very good direction. One other one that I want to mention is we talked about like single source to all targets is a set of demand pairs. We talked about P as an arbitrary set of demand pairs. The S cross S setting is very interesting and very poorly understood. If you have distance preservers where the demand pairs have to be like, I give you a small subset of vertices and they're all pairs within that subset, somehow that just like breaks all of our lower bounds but doesn't improve our upper bounds. That's a setting that I think could use attention. So if you're interested, I definitely recommend that one as like maybe a place to start, or like a place where there might be good theorems to be found. Anyways, quick summary. The advantages of the forbidden structure method are the proofs are simple. I think it's a fairly unified, it's like a good way to unify the area. I was able to like speedrun a fair number of results in the last couple of hours, so thank you for sticking with me through that. That's because of how similar all of the proofs start to feel to each other after a while. And for that reason, I guess I think it's fun. I hope you had fun too, so thanks for your attention. Any last questions? Yes.
So the methods to prove extremal.
Okay, welcome back everyone to the afternoon session. So we have two talks lined up for the session. Our first speaker is Professor Anupam Gupta. So Professor Anupam is currently Silver Professor at the Department of Computer Science at New York University, particularly in algorithms. And throughout he has been one of the stalwarts in the field, which is evident by the fact that he has the highest number of SOTA papers at present. In fact, yeah, you can clap. In fact, if I'm not wrong, by now he has published more than 50 papers in SOTA, and he is the only one to have achieved this milestone. So you can clap once more. So, and in recognition of his work, he was named an ACM Fellow in 2021. So today he is going to talk about combinatorial optimization using comparison oracles. So over to you.
Thank you. The work is all done by other people out here. Right? So I just happen to be around. So this is work. It's work very fresh off the press. It's called combinatorial optimization using comparison oracles, and there's a bunch of us that I won't read out all the names. I'll just mention a couple of names. Demallo and Madhusudan are here. The slides are Madhusudan, so you can thank him for the slides. I'm not audible. Okay.
Request, could you please stand this side, because like this.
Oh, I see.
Gets in the
Hopefully now I'm audible. Yeah, sorry about that, guys. So it's work with a bunch of people, including Demallo and Madhusudan, who are in the audience out here. So you can ask them questions about this as well. And it's a sort of a newish model, and I want to sort of motivate it, and I want to tell you some interesting things that we know about it, and a lot of interesting questions that we don't know how to solve. So hopefully you guys can help us with that as well. Okay. So let me get started. This is classic combinatorial optimization. You're given a family of subsets, feasible subsets. This is what makes it combinatorial. You're given a round set of elements, U, and a family of subsets. And what you want to do is, you are also given a function which maps every subset to a number. And you want to do the standard things. You want to maximize f of s. You want to minimize f of s over feasible sets. So whenever I say feasible set, it will mean something in F. Okay? So it's a standard thing, spanning trees. You're given a graph, you're given a bunch of spanning trees. These are the spanning trees of this graph. You want to find, okay, these are the spanning trees. These are the matchings of this graph. These are ST paths. I can also talk about ST walks, which I will sooner or later. But these are the objects that we're interested in. So these are our feasible sets. And then there'll be this function f, which will map every solution to a value. And there's no no rocket science going on out here. Basically, you might have a linear function. Most of the time, I'll be talking about linear functions. So you're given linear function, there's every element of the ground set has a weight. And so every solution out here has a corresponding total. You're trying to find the max weight spanning tree, the min weight spanning tree, it's all in there. Okay? That's the problem we want to solve. We'll also be interested, but sometimes we'll be interested in submodular functions as well. So let's look at this example. Suppose my ground set was a set of edges, and my feasible sets were cuts. So these are, in this case, look at this cut. So if you look at blue, and you look at the complement of blue, then the cut is given by the edges crossing it. Okay? So if your ground set were the elements, then every cut out here has a corresponding value. And I can talk about the min cut or the max cut. This is one representation. A slightly different representation would be my ground set would be the vertices of the graph. And in that case, the edges that I'm looking at, the weight of the edges will correspond to a submodular function over the vertices. So cuts have two different lives. You can view them as functions of the vertex set, the weight of the edges crossing from this vertex set to the rest, or you can look at the edges which are actually crossing. Two different representations, same objects. Right? Just want to make another trivial point out. This is all that I'm saying. You can look at S as being the set of vertices. The cut function is submodular, and most of you know what submodularity is. It's this decreasing marginal returns property. That if you add U to a smaller set, to a subset, then you get more marginal value than to a larger set. Okay? Good. So this is standard optimization, and we've been doing this pretty much all our lives. And often, and most of the time in fact, and this is what makes it classic, I would say, is that we have access to F by some explicit representation or as a value oracle. I put the solution on and it tells me what the value of this thing is. And as you might guess from the title of my talk, really the thing that we're going to relax is this last part. Well, now I'm going to ask the following question. I can't tell you the value. All I can do is, all you can do is, you can compare to this. It's like that. You give me two solutions, and I'll tell you, is this better, or are they equal to each other? Okay? And I want to solve the same problems. Minimize f of s, maximize f of s. What happens? So that's essentially the model. Right? Now notice that f is a finite set, right? It's got 2 to the n elements in it, if n is the universe size. So I can compare every pair, and I can figure out the best or the worst or whatever. So it's tractable. I mean, it's doable. The question is, what's the number of queries? What is the time taken to solve this problem? Okay? Question clear? Okay. So this is really the question. Can we find the optimal set by comparing only a small number of feasible sets? Okay? And hidden in here are actually these two questions, right? Does there exist a small query solution? It's not clear a priori. And secondly, can I find this small query solution fast? So it's a computation question. So there's the query complexity question and the computational question. So what am I going to do? I'm going to essentially tell you the answer. I'm going to tell you the answer is yes for all linear functions. For the problem as written out here, for the query complexity. The efficient question I can answer only for very special cases. I don't know the complete answer. We can figure it out.
How are you defining a feasible set?
So the feasible set is, it's any set in F. So you're given this, this is basically a setting as before. You are given a set of feasible subsets. This you fix up front. Okay? And the, yeah.
But do you allow to compare non-physical sets also?
No.
But that might be helpful.
That could be helpful in some situations. Yes, definitely. But that's not the model. We can go there.
So what was the motivation?
Okay, well, I'll come to the motivation in a second. Jatin has a question. Answer. Okay.
It's interesting, right? Like in some sense, even with polynomial queries, you're only getting one bit of information.
I'm getting one bit of information. You can say 1.5 bits of information because equality is also allowed, but whatever, 2 bits of information.
Yeah. But whereas like if in the most standard model, like if the weights are like let's say a high bit complexity, then
you might be getting a lot of information. So in some sense, this is telling you something about the intrinsic amount of information you need in order to solve these problems. So, let me give you some motivations. Frankly, yeah.
What is linear? What is linear?
Linear. Oh, f is a linear function. So there's some elements. Every element has a weight. And f of a subset is the sum of all the weights of the elements. Additive. Yeah, additive. Modular, additive, whatever you want to call it. Other questions?
So the family itself might be exponential.
The family typically is exponential, otherwise it's kind of boring.
How are you given the family, the input itself?
Good. So for the query complexity problem, I won't worry about this question. But in general, then you can say, then these questions come up. How are you specify these questions? For the problems we are interested in, there should be some succinct representation of this family. And we'll ask this question essentially for the things that we talked about. Carts, spanning trees, what have you, matchings, for which we understand these things pretty well. Yeah.
Do we really need that the functions are real values? Like all we are using is that it's an order. If we have a comparison.
Right. So,
We don't need them.
what's that?
We do need them to be.
We do need, so in our results we do need them to be real. The sort of question is, do we, let's think of these as real values right now. Let me not try to riff on the fly. Okay. So for me, this problem, just seemed like, once we sort of came up with this question, this to me seemed like the most natural thing ever. Like, dude, why not? Why shouldn't we be studying this thing? We are trying to understand the fundamental nature of computation. This is like one of the basic questions. But, you can justify it, and I'll try to justify it a little bit. And, okay, so this idea that precise, you can assign a value to an object is sometimes, it's not entirely clear. How do you assign, what's the value of this versus that? Sometimes it's sort of difficult to articulate. Sometimes it's, we're talking about objects where it's not entirely clear that you can assign a monetary value to these things. You just like this better than that, and there's a total order on these things. You can also talk about some crowdsourcing thing where you're trying to ask people questions, and there isn't a common baseline. You might think this is 20 versus 10, I might think this is 3 versus 7. And recently there's been a bunch of papers that people have been writing where they say, oh no, we want to ask only pairwise questions. We want to ask only, is something better than something else or not? Now I agree, these are like slightly pseudo motivations. Because, really, who's trying to compare spanning trees? I'm not giving spanning trees to people on the internet and asking them to compare. But I want to understand the power of this model. And recently, maybe I'll give one similar comparison. Recently, there was this interesting work that a bunch of people, including some people in the audience, did, where they were trying to understand finding min cuts using value queries. So I want to understand, what if I give you even less information? I just give you comparison queries. Can you do the same thing? And I'll give you a partial answer to this question. Okay. And yesterday Siddharth was telling me about some stuff in AGT where people are, what's the thing called? Reveal preferences. Where you have this sort of massive value function, but you don't want to articulate it all. You just want to sort of probe it at several places. And using this sort of little bit of information, just get enough information to answer the question that you are interested in. So to some extent, that's what we're trying to do. But frankly, it's just a basic question. We are a bunch of theorists. There's no shame in that. There's, we want to understand this more. There's pride in that. Okay. Okay. So this is the question we're trying to do. Some feasible set. Imagine access to this feasible set. You want to do a small number of comparisons. Okay. So what am I going to tell you? Let me tell you the results. So the first few results are going to be for specific families. And it'll kind of get us warmed up. And these are, again, no rocket science. Nice, clean ideas. Spanning trees, bipartite matchings, SD walks, cuts in the graph. By non-trivial cuts, I just mean, I want to, the empty cut has value 0. That's not the one you should be finding. You should be finding a non-trivial cut, something which cuts the graph into 2 pieces. Okay. Spanning trees can be generalized to matroid bases, bipartite matchings generalized in the natural way to matroid intersection. Okay. So those are the families, the feasible sets. And they have succinct representations. Okay. The functions for these things will be linear. For this thing will be the cut function, which is a modular. Different representation, it would be linear. Let's not worry about that. Okay, so what am I going to show? I'm going to show basically poly-time query and time complexity for these things. Okay. These will be somewhat standard. I'll go over them very quickly. And you will see that sort of classic algorithms that we have can be modified. Sometimes the modification requires a little bit of work to actually achieve these results. This one gets much more interesting. And this result that I'll give is only for, this is sneakily saying this, it's only for the unweighted case. Every edge has weight 1 in the cut. Every non-edge has weight 0. You could ask for weighted min cuts, for which I don't know. This thing is not answering the question. Okay, good.
Can you go back to the last slide?
Absolutely.
So when you say yes for linear functions,
Uh-huh.
so any feasible family, right?
Let me get to that. Uh-huh.
But then suppose it's just all the weights are 1, and you just want to find the largest feasible set, but there is no structure in the feasible sets.
That's okay. So you're talking about all the set family is the set of all is a power set.
Some arbitrary family.
Some arbitrary family. So let me tell you the following. Let me tell you the next thing, and then we'll come back to your question. It's an arbitrary set family. We will not say anything about the running time. Okay, they're linear. It's a sum of weights. This is what I can tell you. That there exist some n squared many queries I can ask and find the optimal set in your set family, the runtime will be exponential. Because it's an arbitrary set family. I don't know how the feasible sets are represented, etc., etc. Even finding the right questions to ask will be very expensive. But there do exist only n squared questions that I can ask and nail down. So you want to find the max weight vertex cover? Sure, I can do that with n squared questions. So it's both because the feasible sets and the questions are hard to ask. Which question should I be asking? And that'll be the tricky part.
So in some sense, one way to understand the bipartite matching cell, for example, would be some query time trade-off or something.
Query time trade-off, okay. So I don't know if we have any query time trade-offs, right?
Okay.
In the arbitrary case, how is the family given?
It's exponential size. Let's say I'll list out all the elements of the family. I'm not worried too much about that. Yeah. So far so good. These are the results that I'm going to, that we know. I won't have enough time to do all that much, but this is what we have. Okay.
It's a very strong. Saying that even if I list out all the independent sets, you will only compare n square pairs.
I'll only compare n squared pairs. So why there exists such a set of comparisons was the surprising part to us.
And hidden in it is some sort of certificate.
Exactly. So suppose I want to just show you that this independent set is the best independent set. I have to prove to you, to give you a proof. And really, this sort of play between the proof and the actual finding of the proof is where the action lies. Okay, good. So I'm going way slower, but that's okay. Please keep asking questions. I don't mean to dissuade you from asking questions. I'm not going to spend all that much time on these things. Maybe let me start. So spanning trees, you can simulate Kruskal's algorithm. Okay. How would you simulate Kruskal's algorithm? Well, suppose you had two edges on a side which share a cycle. Then you could find a spanning tree which contains this but not that edge, and a spanning tree which contains the other way, and you could compare these two. But if there are two edges which if there are two edges like this which don't share a cycle, I can't compare them. But then you think about it, well, actually you never need to compare them. Okay. So actually, this gets you off the ground. At least you can simulate Kruskal's algorithm for spanning trees. Okay. I'm going fast over here, but I just want to give you a general sense of what's happening. Because I want to actually show you something. Ignore all this clearly. Let me figure out how to jump over a bunch of these things. Let me tell you what min is. This is the interesting part, or the more interesting part. I want to find unweighted min cuts using some polynomial number of variables. All I can do is I can just compare min cuts. I can compare cuts. How do I find the min cut? And this bothered us for a long time. And then finally the insight was, at least for unweighted graphs, unweighted min cuts, you can actually reconstruct the graph entirely. Apart from maybe a couple of trivial cases, maybe the 3 cycle and something else. You can't really reconstruct the graph. You can reconstruct the graph using only comparison queries. So let me give you a sense of how you do this. Okay. Unweighted graph, right?
So n square query in total to reconstruct the graph.
Yeah. So I've given you linear up there. Right now I'll sketch only about n squared, and then you can improve. Once we get the general idea, then you can try to see how to do faster. Okay. So here's the main idea. fix any subset of vertices S and any vertex U which is not in S. Using one comparison, using one query, you can figure out how many edges from U are going to S. You know, not how many, but you can compare the edges from U going to S versus the edges from U not going outside S. So you can figure this out. There's, it requires a little calculation, but believe me. So for every vertex outside S, you can ask the question, are the majority of edges going to S or the majority of edges going outside? Or are they equal to each other? The second thing is, as the size S increases, the number of edges from U going to S only grows up. Okay? Good. Let me, okay, good. So here's the algorithm. I'm going to identify sets S1 and S2 such that the number of edges from U going to each SI is about half the edges. So half of the edges from U are going to S1, half of them are going to S2, and they're disjoint. Okay? Good. Suppose I figured this out. So let me not worry about that. So this is U. Here is the set S, S1 let's say, such that half of the edges, rounded down, are going to this. Now, basically what's happening is from U, I know that a majority of edges are going outside this set. I keep growing. Let me go back. Right now, a majority of edges are going outside. Sorry. Going the wrong way. I'm trying to hurry and I'm making it slower. Sorry. Majority of edges still going outside. Oh, majority of edges going inside. I must have just tipped over. So this means that S1 was everything except this last vertex I had. Similarly, I can go from the remainder and figure out S2 to be this tipping point. So now I know that there's an edge going like this at this tipping point. I figured out one edge. Using this kind of thing, I can start figuring out edges of U. And I can figure out the entire neighborhood of U. And if I can figure out it for U, I can figure it out for everybody else. That's the main idea. Okay? So using very simple ideas like this, we were able to figure out, you can reconstruct the graph in this case. You can do it faster, this is what this is trying to say, but you get the main idea. And then if you do some work, you can actually reduce it to an almost linear number of queries using actually ideas that people have done upon and others. These ideas allow us to implement this using a small number of queries and pretty fast. We don't know how to do weighted name count. So I think Shavnik was also on the paper. Yeah.
This tipping business can also happen for weighted graphs as well, right?
Yes, except that it might be the case. Okay. Yeah, so the unfortunate part is that there could be situations where so you can figure out the tipping point.
Maybe you get the support, but that doesn't tell you.
Right. So I'm not even sure we can find the support. So it might be the case that we can't even figure out the support. But even if we figure out the support, it's not clear how to. The weights are going to throw you off. In fact, imagine the support is the complete graph. It's not telling you much. I think I'm pretty much, no, how much time do I have actually?
15 more minutes.
15 more minutes. Oh, okay. Lots of time. I thought it was half an hour. Okay. But anyways, you get the idea for cuts, right? You know, for a set, you can figure out whether a majority of edges are going in or out. You find these tipping points. Those are the edges of your graph. And once you start reconstructing the edges, you can figure out the graph. And you can figure this out fast. Good.
So you figured out one edge, right?
Good.
And
So
then
now
you start with a different.
I look at the remainder of the graph in some sense. And then I find out another edge. I found two edges, then basically you just start peeling off edges one by one. It needs to be done carefully.
So your choice of S1 S2 keeps changing.
Your choice of S1, S2 keeps changing. Here is a different way to do this. Remember, S1 was a maximal set, which contained half the edges rounded down, right? Okay. Now do the following. Take any other vertex of the graph, add it to S1. Suppose there's no tipping going on. There's no edge from U to that guy. But if there is a tipping going on, there's an edge from U to that guy. So you can figure out edges to all the vertices outside S1. And then you go to S2 and you can figure out all the edges to vertices outside S2. And there you have it. So you can do it in several different ways. All roads lead to Rome in this case. We good?
But you reconstructed the entire graph, so the cut just happens to be one application.
Yeah. But I was asking cut queries.
Yeah.
So remember, I was asking cut queries, I want to optimize cuts. If you want to find the MST, you have to ask MST queries. Or what are spanning tree queries. Okay. Good. So let me tell you a little bit in the remaining 12 minutes that I have. Let me tell you a little bit about the general case, which I feel is sort of another very interesting fact to us.
So one question, sorry, like, is there a generic template of reconstructing the graph for all these queries, or it's specific?
I don't know of a general template. Good. Okay. So let me tell you, this is the main theorem. For a family F and an unknown linear weight function W, and let's say the universe size is n, you can solve the minimization problem using so many queries. And forget about the log factors. It's really n times log of the size of the family. And for all interesting families, this is the family size is exponential, so it's n, give or take.
The weights can be negative.
The weights can be negative. Out here, the weights are arbitrarily real values.
So you don't even have monotonicity, like in terms of
exactly.
larger subsets. Okay.
Exactly. There's no monotonicity. Good. So in this generality, you can't hope for an efficient algorithm, right? I mean, independent set is sitting out there. Okay. Even in this generality, you don't hope for a general result. Suppose the weights are either 0 or 1. Just unweighted settings. Now in this case, you can show a slightly stronger result. You can sort all the solutions. You can say these solutions are all smaller than these, are all smaller than these, and so on and so forth, using only n log n comparisons. Good. Okay. And the whole idea behind this is this sort of geometric view. The weight of the set is really, think of all these solutions sitting in this n-dimensional space. So this is really the inner product. The weight is the inner product, right? So the weight of S is equal to the weight of T if and only if the W inner product with S minus T is 0. And then you want to make this greater than, then you put greater than, and so on. Right? So you're really asking this geometric question. We should use the linearity somehow, right? And this is how we're going to use the linearity. We're going to use the geometry. Okay. So let me give you an idea of how to prove this result. And in fact, I'm going to show a weaker bound. And then I'll give you an idea of the stronger bound, but we'll go quick. So I'm going to do insertion sort. The weights are 0, 1. So there are only n possible weights of solutions. At any point in time, I'm going to keep the solutions bucketed into buckets. B1 are all solutions which are equal to, whose weights are all equal. They are smaller than B2, which are some solutions. B3, some solutions. These are not all the solutions yet. There are solutions which are sitting outside, feasible sets which are sitting outside. Good. For each thing, these are just vectors, right? This is the indicator of S, this is the indicator of S prime, S double prime, and so on and so forth. These are just vectors. Look at the affine hull of all these guys. Notice, since all these guys have the same value, any other point which lies on this affine hull also has the same value. Right? I should use the geometry somehow. All points, any other solutions which lie on this guy have the same value. Okay, good. And so the algorithm is going to be this infer or insert algorithm. Suppose a new set arrives. Just consider the sets in any order. Look at the next set. If this set is contained in one of these affine hulls, I know its value. I don't need any comparisons. Right? If it lies there, or it lies there, or it lies there, I know its value. Otherwise, suppose none of these things happen. What are the options? Either S has a weight which is not equal to any of these, or it's equal to one of these, let's say, but the affine hull did not, it didn't lie in this affine hull. Suppose that's the case, then the dimension of this affine hull will go up by 1. This can happen only n times. Okay? Otherwise, I'll create a new bucket. This can happen only n times. You see where this is going. That's it. So either I increase the dimension of one of these hulls, or I increase the number of buckets. Very simple idea. Very clean. Okay. Yeah. We pay for inserts. They can be only n plus n squared inserts. There are so many buckets, and so many buckets, so many times the affine hull can go up. Good. Suppose I want to do slightly better. Let me just give you a sense of how to do slightly better. I was maintaining the affine hull for each of these guys. Right? Why affine hull? I know these two guys have the same value. So the weight vector is orthogonal to the difference of these two guys. Remember that picture that we had in the previous slide? Where there was this. There was the 1s minus 1t was orthogonal to w. Right? So the weight vector is orthogonal to this, the weight vector is orthogonal to this. But why am I keeping different affine hulls? All these differences, this difference is orthogonal to the weight vector. But these differences are also orthogonal to the weight vector. So I just need to maintain the affine hull of all these individual differences within buckets. Really, I need to maintain one global affine hull. Or rather, one global direction which is orthogonal to W. And translates of this will give these affine hulls. So now the dimension only needs to go up n times. You need only so many new buckets and so many dimension increases. This will give you the linear result.
What is the dimension increase in this context?
Good. So what is the dimension increase? Suppose I find out that this new solution I have has the same weight as these guys. So it doesn't lie on this affine hull, right? So it doesn't lie on this thing. So it will increase the dimension by 1.
Right, so it's like a translation.
It's just, all these are translates of the same subspace. Okay, good. Okay. All these were for the 0, 1 case. You can do the same thing for bounded weight vectors. For the general case, I'm not bounding the weights at all. These could be arbitrary reals. Okay. So the idea out here is to use conic hulls. Somehow we were just using the equality comparisons were all we were using so far. In each of these affine hulls, inequalities were just being used to maintain these buckets. But, I didn't even need that. I just needed, these guys are not equal to these guys, are not equal to these guys. Okay. But really, we have more information. And here is the main idea. And then we can connect it to some very nice results of Kane, Lovett, Moran, and John on something called the inference dimension. But the main idea is this. Let me tell you the main idea. This is the weight vector. I don't know the weight vector, right? All I know is comparisons. So the main idea is that I need to relate this to kind of a certificate of optimality. So the query complexity of finding S star is lower bounded by the smallest certificate of optimality. Okay, what's one certificate of optimality? Consider the following certificate of optimality. Suppose I could show you that S1 is better than S2, S2 is better than S3, S3 is better than S4. Okay. Then, here is something that you can do. Ignore all the text down there. S3 is better than S2, right? So this vector has a positive correlation with W. This vector also has a positive correlation with W. So everything in this cone has more weight than S1. So I can throw away these suckers out here. So what do I want? I want these sequences, S1, S2, S3, S4, such that each guy has more weight than the previous guy. And I want a short such sequence. The shortest such sequence is called the conic dimension. We call it the conic dimension. It's very closely related to this idea of inference dimension that these guys use. If you don't know this stuff, don't worry about it. You just understood pretty much the main idea behind it. Okay. So now really the question is, I want to come up with certificates like this. And what's an algorithm to find this? And this is the last thing I'll say, and then I'll stop. So are there small such certificates? A set of points is conically independent if S3 was not contained in the cone defined by S1, S2. S4 was not contained in the cone defined by this sequence. Okay. The conic dimension is the size of the largest conically independent sequence. You can show that the conic dimension is small. And there is so there's a certificate of small size, but let me give you the algorithm I promised. So here's the algorithm, and you'll see that it's an inefficient algorithm. K is like n log n. If the number of solutions remaining in my bag is at most like K, just brute force over them. Just compare all of them. Otherwise, sample a small set of these solutions. I have many solutions left, right? Sample about K of them. You're sampling each guy with probability K over F. There are F guys remaining, so this goes away. About K guys are being sampled. Sort all of them. This gives you a sequence. S1 has weight less than S2, has had weight less than S3, and so on and so forth. Draw this picture. for that sequence. Throw away all the guys who are implied in this way. Repeat. So you have fewer solutions. I don't know a compact representation of the solutions that are remaining. It's some crazy mess. But what we can argue is that in each time, about half the solutions are eliminated in expectation. Okay. The proof, I'm not going to show you, it's a very, if you guys have seen Kargar's MST algorithm, there's a proof out there. I think of it as a Kargar proof. David Kargar is making yet another appearance in his graph algorithms workshop. What a surprise. But essentially, it's a very Kargar style proof that you can throw away about half of the solutions every time. The proof is, there's some proof by picture, but it'll take me too long to explain this. So let me just skip over all this. The algorithm is easy. Once you set up this whole infrastructure of conic dimension. But I don't know how to make it efficient. Even for families that I care about, like weighted cuts, which is perhaps the
It boils down to sampling up, like after you've
exactly.
many.
Once you've filtered out all these dominated solutions, what is the structure of the remaining?
You have to even sample from it.
You need to even sample from it. So suppose I gave you a sampling oracle and an optimization oracle. What can you do? We know a little bit. We can show that as long as you can give me short certificates, you can use some ellipsoid technology to get a good algorithm. But let me stop here. Let me just mention the open questions. For what classes of F can we get just comparison-based algorithms? In particular, min-cut and weighted graphs, which I've mentioned 3 times, I'll mention a 4th time. Compare perfect matchings to find the best perfect matching. I don't know how to do that. I know how to compare matchings to find the best, max weight matching or something. But compare perfect matchings to find the best perfect matching, I don't know how to do. And then I talked about linear functions. What about submodular optimization? For instance, here is one concrete question that I mentioned yesterday to some of you. I want to get a half approximation for non-monotone submodular maximization. I know a 1 over E. 1/4 is easy, just take a random set. Local search will give you 1 over 3. Random greedy will give you 1 over E. That requires a little bit of work. But 1/2 is the boundary. 1/2 is what I hope is the answer, but I don't know. So modular minimization, I don't know how to do it. But that's also related to weighted graphs. So it's so that's the main idea. I gave this new model, which I really like. I hope you like it too. It has some applications, but really the application as a theorist is to understand the power of this model. For cuts, we can do something. For general things, we can give surprising query complexity bounds. I find them surprising. But then there's a lot of open questions, which I don't know how to solve. So with that, thanks. Yeah,
Is the complete construction of the graph necessary? Does it say that is there a lower bound of n square?
So it's
Yeah, thanks, Sagnik, Arindam, Siddharth, everyone. Unfortunately, due to this IISco, I was not able to come, but I really wanted to be there. It's really unfortunate, but but I'll give the talk online. So let's start with the talk. I also cannot see you, anyone. So I mean, you can Sagnik or anyone, you can ask any questions in the middle if there are any. Okay. So the title of the talk is Improved to Approximate Shortest Path for Closed Vertex Pair. Okay. So in this particular problem, what we want to do is we want to find. Can you anyone? Can you hear me? So you want to find all pair shortest path in an undirected and unweighted graph G. Okay, this is the main problem. Okay, and for this particular problem, there is a very simple combinatorial algorithm. What you do is you just run the bat first search from each vertex in the graph, and the running time of that algorithm is order mn. Okay, and there is again, remember, this is undirected and unweighted. Okay, so this is this is not directed and it's not weighted. So undirected and unweighted. Okay, and there is a fast matrix multiplication algorithm, an elegant algorithm by Seidel in 1995 that gives a running time of n raised to omega, where omega is the minimum amount of n raised to omega is the minimum amount of time to multiply two n cross n matrices. Okay, so these, I mean, the combinatorial as well as the algorithm that uses fast matrix multiplication, the running time is super quadratic. And what we want to do is we want to achieve a near quadratic time. Okay. And to achieve near quadratic time, we'll introduce some approximations. Okay, so what is that? Okay, so before that, let me give you some notation. Let est of s comma t be the estimate of shortest path from s to t computed by our algorithm. Okay, and let st denote the actual shortest path, and mod of st, that is the length of the shortest path. Okay, so if our algorithm, if for all pairs, if for all st pairs, it computes an estimate which is greater than the actual shortest path, but less than alpha times the shortest path plus beta, where alpha is greater than equal to 1 and beta is greater than equal to 0, then we say that this algorithm is alpha beta approximate. So alpha is the multiplicative factor and beta is the additive factor. So some short forms. Well, an algorithm which is k comma 0 approximate, it is basically multiplicative k approximate. So we just drop 0 and say this is a k approximate APSP. Similarly, an algorithm which is 1 comma k approximate, it is basically additive k approximate. So we just write plus k approximate for this. So in this talk, my main focus is to approximate APSP. Okay, but then why are additive approximation even required? So let's see. Okay, so here are some results on to approximate APSP and also plus to approximate APSP. Okay, so this is an algorithm by a very influential algorithm by Enver, Chekuri, Indik, and Motwani in 1996. They gave a plus to approximate algorithm for APSP, and the running time is n raised to 2.5. I mean, tilde notation, this tilde hides polylog factors. So n raised to 2.5. And this is the very simple observation that you can see, that a plus k approximate APSP also implies two approximation for all pairs of vertices that are at least k apart. Okay. In particular, this plus 2 approximation implies a 2 approximation for all pairs that are at least 2 apart. And what about the vertices which are at distance 1? Well, that you can actually find very easily. They are just the neighbors. So this algorithm also implies 2 approximate APSP, and the running time remains the same. Next, there was an algorithm, again, an inflation algorithm by Harperin and Zick in 1996. They gave a plus k approximation of plus k approximate APSP, and the running time was n raised to 2 plus some order of 1 by k. Okay. Again, what does this give? Again, this gives a 2 approximation of a all-pair shortest path, but only for pairs which are at least k apart, using this observation. By the way, can you see my pointer or my this? Yes. Yes. So this gives a plus. It gives you a 2 approximation, And now for all pairs, there are at least k apart. Okay, so now let's go to two approximations only. Okay, so this is the algorithm by Dor, Halperin, and Zwick. In their paper, if you set k is equal to 2, then you'll get a running term of n raised to 7 by 3. And there are some other results also by Cohen and Zwick. They get a 2 approximation. Again, the running time is n raised to 3 by 2 into n raised to 1 by 2. Another one by Baswana and Kavita, 2 approximation, that their running time was m square root n plus n square. Okay, so if you see all these results, okay, they have a maximum running time of n raised to 2.5. Okay, 1 second, just one minute. Alexa, stop. So most of these results have a maximum running time of n raised to 2.5. Okay, but the best running time is n raised to 7 by 3. So if you will get n raised to 2.5, but the best is n raised to 7 by 3. N raised to 7 by 3. And in the papers and around 2007, 8, 9, this was a very active field of research. But then this problem became dormant, and there are some recent progress. So what is the recent progress? So this is the best algorithm known, it was known till recently. In 2023, Roditive designed a 2 approximate APSP with a running time of n raised to 2.25. And later, this is in last year's 2024 SODA, the two sets of people, Dory, Forrester, Kirkpatrick, Nazari, and Williams, and Saha and Ye. Again, they also designed a 2 approximate APSP, and this running time is, I mean, it's very, very small, n raised to 2.031, but this uses fast matrix multiplication. Okay, so this result is combinatorial. The result here uses matrix multiplication. And this is the most important problem in this particular field. Can you compute 2 approximate APSP in n square time? Okay, so we can get something which is very, very close to 2, but can you get 2? This is the important problem. Okay. And if you cannot get 2, what kind of approximation can you achieve in order n square time? Okay, so I'll say what do I mean by this approximation? Okay. So this was the result by Dor, Halperin, and Zwick, and I said that well, you can get plus k approximate in this time, but this implies that you also get 2 approximate for all pairs that are at least k apart. Okay. If you set k is equal to log n, then this running time would be n square. And this algorithm gives 2 approximation, the running time n square, but it works only for pairs that are at least log n apart. Okay. And there are some other algorithms also. Like there is an algorithm by Burman and Kashi Vishwanath. They also get n squared, but their approximation factor is 2,1, not 2. So the main thing here is, can you get rid of this one? If I just want n squared time, okay, the best is I can get 2, but only for all pairs that are log n apart. Okay, and this algorithm, it works for all pairs, but there is the additive one factor. So this is the another problem. Can you compute 2 approximate APSP for all pairs whose distance is at least small o of log n apart? Log n I know how to do in n square time, but can you do anything less than log n? Okay, so these are the two problems. The first is I have tried it a lot. I don't know how to solve it, but the second one is what I could solve. Okay. So the result is we can find 2 approximate APSP for all pairs that are at least order log n apart. So the previous best was this, which got to log n, and this gets to log n. And this is a general result. We can find 2 approximate APSP for all pairs which are at least order log k apart in order 2 raised to 1 by k time. So if you get set k is equal to log n, you'll get this running time, and here you will get log n. Okay, so this is the main result. I hope I have tried to tell you what are all the known results which were there. Put this result into context. Okay, if you have any questions, you can ask. So this is the outline of the talk. I'll not be able to give you the entire whatever the whole paper in its entirety, but I'll try to tell you the main parts of the paper. So the first part is what is the plan to solve this problem, and then a false or flawed approach to execute this plan. Okay. And the third part would be a new tool that kind of mitigates this false approach. Okay, and then we can execute our plan. So the first thing is, what is my plan? Okay. So first of all, what I'll do is I'll use previous results. There is a result by Baswana and Kavita in 2006 that they showed that we can find two approximate APSP in order m square root n plus n square time. What you can do is you can use this algorithm to find two approximate APSP for at least some pairs. And what are those pairs? Well, if the degree of all the vertices on the ST path is less than square root n, then we can actually directly use this algorithm. Okay. What we'll do is we'll delete all the vertices with degree greater than square root n. The resulting graph has n square root n edges because you have deleted all the high degree edges. And now you run the algorithm of Baswana and Kavita. And now this algorithm will run in n square time. So this is the first part of my plan. So you just get rid of all these pairs. And now I look at only pairs which have this high degree assumption. What is the high degree assumption? The ST path contains at least one vertex of degree order square root n. Okay, so this is the assumption that we'll work with from now on. Now, if you see, I mean, if you assume that, okay, there is a vertex on this path which has a very high degree, I hope you see that maybe I'll do some kind of sampling. Okay, and this is actually what we do, and this is what is actually done in most of the papers. Okay, so what you do is you let's say you look at let's say y0 is vertices in the graph. Okay, and from y0 what you do is you sample vertices into y1 with probability half. So y0 contains all the vertices, which means each vertex is in y0 with probability 1, and the number of vertices in y0 is n. Y1 contains each vertex in y1 is there with probability 1 by 2, and there are n by 2 vertices in y1. Similarly, you find y2 by sampling each vertex in y1 with probability half. So the probability of y2 is 1 by 2 square, and the number of vertices is n by 2 square, and so on and so forth. Okay, and the number of levels here is log n. And this is normally, you would have seen this in some papers. This is called nested vertex sampling. So we'll not use this, but you will use an approach which is nearly similar. Now what I mean, here we have again y0, which contains all the vertices in the graph, but y1 vertices in y1 are sampled from y0 with probability 1 by 2 raised to 2 raised to 1. Okay, so this is the probability the vertex appears in y1 with this probability, and the number of vertices is this. And for every subsequent I, the vertices in yi are sampled from yi minus 1 with probability 1 by 2 raised to 2 raised to I minus 1. And the picture looks something like this. And our last level is log log n minus 1. It is not log log, it's log log n minus 1. Okay. Now, I mean, if you see this particular term, 1 by 2 raised to 2 raised to log log n minus 1, well, this is basically square root n. So this term is actually 1 by square root n. And this here is n by square root n, which basically is square root n. So the number of vertices in log log n minus 1 is roughly order square root n. Again, everything here is with high probability. Okay, so this is my sampling procedure. And now I hope you see why how does this sampling procedure kind of will be useful. So let us assume, and since we have this high degree assumption, let's assume that there is a vertex X on the ST path with a high degree, with a degree greater than square root n. This is our high degree assumption. So let's assume this X is there. With a high probability, I claim that there is a vertex Y which is adjacent to X, because this X has high degree. Okay, so this is a vertex Y, and this Y would be in Y log log n minus 1. Now this fact will enable us to define some very good notations. Okay, and this is my notation. This is a new notations that we are defining. Okay, it is not there previously. So let A log log n minus 1 be the vertex nearest to S which has a neighbor in y log log n minus 1. Or maybe a log log n 1 minus 1 itself is in y log log n. That is also fine with me. Okay. So and let's call that neighbor u log log n minus 1. So this vertex a log log n minus 1 is the vertex which is nearest to s, such that it has a neighbor in u log log n, in y log log n minus 1. And why should such a vertex exist? Because this x exists. That's why we know that such a vertex will exist. So here we are using this high degree assumption. Okay. One more thing is, if you see, since I have found the nearest vertex, which is the nearest vertex, which has a neighbor in y log log n minus 1, I claim that all the vertices in this particular part of this ST path, they should have low degree. In particular, I claim that all these vertices in this blue line, except a log log n minus 1, they have degree less than square root n. Well, why? Because if there is any vertex here which has a degree square root n, then with high probability, one of its neighbor would be in y log log n minus 1. So that vertex would. So all these vertices actually have low degree. Low degree in the sense that they have degree order square root n. Similarly, I found a nearest vertex from the S side. Now I'll find a nearest vertex from the T side. So B log log n minus 1 be the vertex nearest to T, which has a neighbor in y log log n minus 1. And let's call this vertex V log log n. So I hope this, again, because of high degree assumption, I'm sure to find these vertices. Okay, such vertices, not find, I should say that such vertices should exist on this path. What we will show, and we will design algorithms that will give us a very, very good estimate between u log log n minus 1 and v log log n minus 1. In particular, we will design algorithms such that the estimate between u log log n minus 1 and v log log n minus 1 is less than equal to the length of this path between a log log n minus 1 and b log log n minus 1 plus 4. So we get some additive factor, but it is not very bad. It's just plus 4. Okay. So this is actually the base case, and actually I'll not go into the base case, but I want to just tell you how does the plan actually moves forward. Okay, like a log log n minus 1, I can find another vertex which is a log log n minus a log log n minus 2. So what is a log log n minus 2? It's a vertex which is nearest to s, such that it has a neighbor in y log log n minus 2. So this is the vertex which is nearest to s, and its neighbor is in y log log n minus 2, and this is u log log n minus 2. Similarly, b log log n minus 2 is the vertex which is nearest to t, which has a neighbor in y log log n minus 2. And this vertex is, I define it to be v log log n minus 2. Again, what we will show, we'll design algorithm such that gradually, I mean, you'll get a good approximation between these two vertices also, u log log n minus 2 and v log log n minus 2. Their estimate would be less than equal to this path, the length of a log log n minus 2 to b log log n minus 2 plus 8. So gradually you see the approximation is kind of deteriorating, but it is actually fine. It is will able to contain the deterioration. Okay, in general, this is what I want to show. In general, let's say AI is the vertex which is nearest to S on this ST path, such that its neighbor is in YI. And let's call this neighbor UI. And BI is the vertex which is nearest to T on this ST path, which has a neighbor in YI. And let's say this vertex is VI. Again, I want to claim that such a vertex must exist. This is because of high degree assumption and the fact that the vertex sampling is nested. Okay, all these vertices must exist on this path. One more thing is all the vertices, if you look at vertices on this blue line and here also on this blue line, all these vertices should have low degree. Low degree in the sense it is degree less than 2 raised to 2 raised to I. Because it is the nearest vertex from S. AI is the nearest vertex from S whose neighbor is in YI. So all these vertices should have low degree in this. I mean, low degree, I mean, is less than 2 raised to 2 raised to I. Okay. And what we want to show is the following. Again, we'll try to show this, that estimate, we design an algorithm such that estimate between UI and VI is less than equal to the distance between AI and BI plus 4 log log n minus I. So this is actually our plan. Gradually, we want to get an estimate between, first I'll get an estimate between u log log n minus 1 and v log log n minus 1, then u log log n minus 2 and v log log n minus 2, and go towards S. If we are able to do this, if our plan is successful, okay, then my claim is estimate between u0 and v0 is less than equal to a0 b0 plus 4 log log n. But what is u0? Well, u0 is the vertex which is nearest to S, which is a neighbor in y0, but y0, and even S itself is actually one of the candidates. So u0 and a0, because S itself is in y0. So I claim that u0 and a0 will be equal to S, and v0 and b0 will be equal to t, which means the estimate between S and t will be less than equal to the shortest path between S and t plus 4 log log n. Okay, if this plan is correct, okay, if you are able to execute this, it's not easy to execute, but if this you are able to do this, then we'll get actually a additive 4 log log n approximation of the ST path, okay, which is actually wrong, but because you cannot get in n square time, but we'll go to there. But the main thing is we'll get a 2 approximation of ST path if the length between S and T, if the length of between S and T is greater than 4 log log n. Okay, so this is my plan. I want to actually find the estimate between UI and VI. Okay. So one more notations that I have, and after that we'll see how to execute this plan. Okay, so this is the notation which is again there in this in literature. If you read the papers on related to this area. So let pivot I of u be the vertex of yi which is nearest to you. Okay, so let's say this is the vertex u, and pivot I of u, this is the vertex of yi which is nearest to you. Okay, ball I of u, so let ball I of u be the set of all the vertices that are closer to you than pivot I of u. So if you look at all these vertices, okay, all these vertices are closer to you than pivot I of u. So they are in this ball, and I define it to be ball I of u. Okay. One very nice observation is that the number of vertices in ball I of u is actually very small. It is 2 raised to 2 raised to I, because the vertices in AI are sampled with probability actually 1 divided by 2 raised to 2 raised to I. So the number of vertices in this ball is actually very small. Why? Because if the number of vertices in this ball is greater than 2 raised to 2 raised to I, then you can show that one of this vertex would be in yi. So you can actually decrease the distance between u and pivot I of u. So the number of vertices in this ball is actually quite small. Okay. Now using this observation, and there are some other observation also, what we can show is that for each I from 0 to log log n minus 1, and for each vertex u in this graph, we can find pivot I of u and ball I of u in n square time. Okay, and this just uses the fact that the number of vertices in this ball is very small. Okay, so you can find pivot I of u for all the vertices and ball I of u also for all vertices in n square time. So we'll not go into this. This is actually known in literature. Okay. In particular, I want you to see this pivot I of u. I defined AI to be AI is the vertex which is nearest to S. Okay, such that its neighbor is in yi. So ui is in yi. So ui is actually pivot I of AI. Similarly, AI plus 1 is the vertex which is nearest to S, such that its neighbor is in yi plus 1. So ui plus 1 is actually pivot I plus 1 of AI plus 1, and so on and so forth. Okay, so this is all the notations that I wanted. And now what I'll do is I'll assume something which kind of will execute this plan. Okay, the plan that I have. And the assumption is actually false. This is the main part. This assumption is false. One second. So this assumption is false. Okay, this is what I want you to understand. And what is the assumption? Well, we'll assume that ball I plus 1 of ui contains ui plus 1. Okay, now why is this false? remember this ui plus 1, the way we have defined, this was in y of I plus 1. And by definition, ball I plus 1, this I plus 1 of ui, it cannot contain any vertex from yi plus 1. Okay. So how did we define ball of ball I plus 1? Well, first we find pivot I plus 1 of ui, and then we look at all the vertices which are closer to ui than pivot of I plus 1. So by definition, it cannot contain any vertex from yi plus 1. So clearly this ui plus 1 is cannot be there in this ball, but this is exactly what we will assume. Later we will see how to kind of get rid of this assumption. But let's kind of assume this as of now. Okay, so this is what we want to prove. We want to prove that estimate between ui and vi is less than equal to ai bi plus 4 log n minus I. So let's assume using induction, though I did not tell you the base case, but let's assume that you can do the base case also. And let's assume that using induction, we have found this, we have found the estimate between ui plus 1 and vi plus 1. And this is less than equal to ai plus 1 bi plus 1 plus 4 log n minus I plus 1. And now we have to find the estimate between ui and vi. So let's see how to do this. And this is the most difficult part of this particular, there are other things also, but I hope you understand what is the difficulty in getting this estimate. Okay. So my first part, what I'll do is will execute Dijkstra's algorithm from ui plus 1 in a small graph. And this is very, very important that I want to run Dijkstra's algorithm. Now remember this, the graph which is given to me is unweighted, but I'll make graph which is weighted. That's why I'm running Dijkstra's algorithm. Okay, so we will execute Dijkstra's algorithm from ui plus 1 in a small graph. And I want this graph to be small because I want to ensure that the running time is on n square. Everything is a kind of hinged on the fact that I want n square running time. Okay, that's why I'm doing all these things. Okay, so let's see how to do this. Okay, so what I'll do is I'll make a graph from which and in that graph I'll run the Dijkstra's algorithm from ui plus 1, and this will give me a estimate between ui plus 1 and vi. So let's see how to construct this graph. So first of all, what I'll do is I'll delete all the edges from G whose both the endpoint have high degree. So they have degree, let's say 2 raised to 2 raised to I plus 1. In particular, I claim that the edges which are here from S to AI plus 1. Remember that I had argued that these vertices actually would have low degree. So all these vertices on this path, they have degree actually less than 2 raised to 2 raised to I plus 1. Similarly, from BI plus 1 to T also, the vertices here, they also have low degree. So you will not be deleting these edges, but you may delete the edges which is between AI and BI. And this is actually the difficulty. Okay, I mean I have to delete all these edges because I don't want my graph to be the size of my graph should not be huge. Okay, that is why I'm deleting all these edges. Okay, I mean it would have been so nice if I could have estimate the path from UI plus 1. I would have done Dijkstra's from this in this whole graph, so I would have found this path. But I actually cannot use I cannot use vertices which are in the middle because they have high degree. And if I use these vertices in this graph, then my running time would be greater than n square. So this is the main challenge. Okay, so I have to I delete all these vertices. Second is I add an edge from ui plus 1 to all the other vertices. Let's say ui from ui plus 1 to x with the weight which is equal to whatever my current estimate is. In particular, I'll add an edge from ui plus 1 to vi plus 1, and the weight of this particular edge is my current estimate between ui plus 1 and vi plus 1. And you are not adding a lot of edges here, you're just adding n edges here. And lastly, what I'll do is I'll add an edge from x to its adjacent vertex pivot I plus 1 of x, which is in yi plus 1, and pivot I of x, which is in yi, if such an edge exists. In particular, in this third step, I'll add these yellow edges. Okay, if it exists, I'll add these edges. Now, I want you to kind of remember that I know that AI plus 1, UI plus 1, AI, UI, all these vertices exist, but I actually don't know these vertices. Yeah. because I do not know the ST path. My whole point is I want to find an shortest path. Okay, so I know that these vertices exist, but I do not know these vertices. That's why what I'll do is I'll run this algorithm for all the vertices, for all the vertices in yi and for all I. Okay, so and I'm sure that I will execute it for ui plus 1 also, because this is in ui plus 1 is in yi plus 1. Okay, so I'll run this algorithm for all I and for all the vertices in yi, and my claim is that the running time of this algorithm is order n square. We have been very diligent. We have removed all the high degree vertices, and if you do the calculation correctly, you will see that the running time of this algorithm is order n square. Okay, so what do we get? Well, when we run Dijkstra's algorithm, well, this path from ui plus 1 to vi plus 1, then this edge, then this edge, and then this edge. This path is there in G of ui plus 1. So I'll get an estimate between ui plus 1 and vi, where this is the weight of the first edge, then 1, this is 1, this is 1, and this is the length of bi plus 1 and vi. Okay. And what is this? Well, by induction hypothesis, we already know that this is ai plus 1, vi plus 1 plus 4 log n minus I plus 1. Okay, and if you do the calculation correctly, you will get this. Okay, so now what we have done is we have found a very good estimate between ui plus 1 and vi. And now what I want to do is I want to find the estimate between ui and vi. This is my main task. I want to find a very good estimate between ui and vi. And currently we have a good estimate between ui plus 1 and vi. Okay, and here we will use the false assumption. What is my false assumption? That ball I plus 1 of ui contains ui plus 1. Okay, and how do you use this false assumption? For each x and y in yi cross yi, and for each w in ball I plus 1 of x, I will estimate the distance between x and y using w. In particular, if you set x to be ui and y to be vi, both are in yi, and w is ui plus 1, then what I'll get is I'll estimate the distance between ui and vi using ui plus 1. Okay, and I've assumed that this is my false assumption that ui plus 1 is in the ball. Now, again, there is no better way to do this. I mean, you cannot actually find the shortest path from ui plus 1 using this path, because this path contains high degree vertices. And I cannot do Dijkstra's. I mean, I cannot run even Dijkstra's or even BFS, because then my running time would be greater than n squared. Okay. So what do I get? Okay, before that, again, this is my very simple algorithm. And again, I can ensure that the running time of this algorithm is order n square. Why? Because the number of vertices here is less, and the number of vertices in the ball is also less. That is the main thing. Okay, and you can ensure that the running of this algorithm is order n square. Okay, so this is my assumption. This ball I plus 1 of ui, it contains ui. I'm just going to use this to get a very good estimate. Okay, so since this is in the ball, I would have estimated the distance between ui plus 1, ui and vi using ui plus 1. So the estimate between ui and vi is less than the estimate between ui and ui plus 1 plus the estimate between ui plus 1 and vi. Okay, but ui plus 1 by my assumption is in the ball I plus 1 of ui. So I know its exact distance. I know its distance exactly because I've computed the ball and I know the distance between ui to all the vertices in the ball. And what about this? Well, this is the first part of my algorithm. So this, I know it is less than equal to whatever we got in the first part. And again, if you do the calculation, you'll get this. Okay, and by this we are kind of done. Okay, done in the sense that if we have this false assumption, then you will be able to execute this approach. Okay, so now the third part is I want to get rid of this false assumption. Okay, so before I go to the third part, any questions till here? Okay. Okay, so this is the last part of my talk. What I want to do is I want to get rid of this false assumption. This is clearly false. Ui plus 1 cannot lie inside the ball of ui, ball I plus 1 of ui. Okay. In particular, this ball, I mean, in reality, this ui can be very, very far away from ui plus 1. Okay. And that's why this ball also can be very, very far away. Okay. So you'll not be able to execute this approach if this is the case. I mean, and this will always be the case. I mean, it will be far away. Okay. But if you can ensure that ball I plus 1 of ui is close to ui plus 1. Okay. If you can ensure this, 1 second, 1 second. Okay. So if you can ensure that ball I plus 1 of ui is close to ui plus 1, in the sense that, I mean, this is ui plus 1, and if you see this ball, the distance between this vertex and ui plus 1 is very, very small. In this case, it is less than equal to 7. So if you can ensure that this ball I plus 1 is very, very close to ui, even then you can implement this approach. And we are not going to see what that approach is, but I hope you see that maybe there is some hope. But if this ball is very, very far away, then you don't know. Okay. But can you ensure even this very weak condition, and this I could say as weak closeness condition. Okay. So this ball does not contain ui, but it is very point here, and ui plus 1 is less than equal to 6. Okay. So can you ensure even this? And the main part is, well, yes, you can do this. And this is the main contribution of our paper. Okay. So this is what we will do next. Okay. This is the last part. Okay. This is the main contribution that we can actually ensure this weak closeness condition. Okay. And how do you do that? Well, this is the main algorithm in our paper, and I'll try to explain what this particular lemma is saying. Okay, so we design an algorithm which I call ensure closeness, and what it does is that after the execution of this algorithm ensure closeness, either we have estimated the distance between s and t, and it is too approximate. Okay, or for all I from 0 to log n minus 1, the difference between the distance sai and s pivot I of s is less than equal to 3, or this difference between t of bi and t pivot I of t is less than equal to 3. And moreover, this algorithm is quite fast. Its running time is n square. Okay. Now I want you to just take a look what this particular lemma is saying. Okay. What it is saying is either you get two approximate shortest path of between S and T, or there is something good is going to happen. Okay, this is how I want you to interpret. Okay, either you get this, or these two things actually they say that, well, something good is going to happen. And let me tell you what I mean pictorially. Okay, so let's say this is pivot I of S. This is the nearest vertex to S, which is in yi. Okay. So now look at this circle where the distance between with radius s and pivot I of s. In particular, the distance between this vertex and this particular vertex on the ST path is the distance between s and pivot I of s. What this particular lemma is saying that SAI minus this distance is less than equal to 3. In particular, the distance between this and this is less than equal to 3. This is what it is saying. Similarly, the distance between this and this vertex is less than equal to 3. And this is true for all I. Okay, so we'll not prove this particular lemma in this talk, but this is one of the, I mean, one of the main contributions in our paper, and it's not very hard also to actually get this. Okay, the main thing is actually to come up with this particular lemma. Okay, the algorithm is not hard. Coming up with this formulation is actually hard. Okay, so now I claim that this lemma, this algorithm for which we have proven this lemma, this actually ensures weak closeness condition. So what was the weak closeness condition? That ball I plus 1 of ui, this ball is very, very close to ui plus 1. Okay. In particular, the distance between this vertex and this vertex is less than equal to 6. Okay. Let's assume for contradiction that actually ball I plus 1 of ui is very, very far away. Let's assume that the distance between this vertex and this vertex is greater than 6. Well, in this case, let's just step back and see how we have created this ball. Okay. So remember, we have created this ball by doing the following. We found the nearest vertex in yi plus 1 ui. So this is the vertex which is nearest to ui and which is in yi plus 1. Let's call this pivot I plus 1 of ui. Okay. And then we took all the vertices which are closer to ui than pivot I plus 1 of ui. So this is my ball. Okay. In particular, what I want you to understand that this vertex is just a distance 1 away from this ball. Okay. So pivot I plus 1 of ui just lies outside the ball, I plus 1 of ui. Okay. And pivot I plus 1 of ui is in yi plus 1. Okay. And my claim is, and this I hope you it's that easy to see, that pivot I plus 1 of ui is also a candidate for pivot I of s. So this vertex can also be pivot I of x. Either this is pivot I of s, or maybe there is another vertex which is at the same distance, which is pivot I of s, or maybe there is some vertex which is nearer to s, which is pivot I plus 1 of s. I don't know, but I mean, pivot of I plus 1 of s cannot be at a distance greater than the distance between s and pivot I plus 1 of ui. Okay. And I claim that this is actually the worst case, and you can take it from me that in the worst case, actually, let's assume that this is pivot I plus 1 of s. Okay. Which means what? Well, which means that if you look at this distance, okay, distance between s and pivot I plus 1 of s, which means if you look at this distance from s to pivot I of s, which is here. Okay. Well, I know the distance between this and this is greater than 6. This is by assumption. We assume that this is greater than 6, which this implies that the distance between this vertex and this vertex should be greater than equal to 4. Because this vertex is just outside the ball. Okay. And this is a contradiction, because we assumed this implies that the difference between s of ai plus 1 minus s pivot I plus 1 of s is greater than 4. But this contradicts the algorithm, the property of the algorithm ensure closeness. So which says that s of ai plus 1 minus s pivot I plus 1 of s is less than equal to 3. Okay. And that's it. I mean, that's it. We have arrived at a contradiction, and our algorithm ensure closeness actually ensures this weak closeness condition. So what I have not told you in this talk is how do you get this particular magical lemma. But believe me, I mean, this actually is not very hard. It's actually easy. Once you formulate this, it's just a very easy thing to prove. Okay, so this is not done in this talk. And how do you extend the very trivial approach that we saw at the first part of the paper? That is also not done in this talk, but you can refer to the paper. I hope that I have given you enough intuition as to what is happening in the paper. Okay, and that's it from me. Thank you so much.
Hello everyone. It's my pleasure to introduce Professor Kavita as our next speaker. Kavita completed her PhD from TIFR and went to Max Planck for a postdoc. After her postdoc, she joined our department, CSA, as a faculty member for a few years, after which she moved to TIFR as a faculty member, where she is also the Dean of the School of Technology and Computer Science. She'll be talking about assignments, arborescences, and popularity today. Without further delay, I'll hand it over to Professor Kavita.
Thank you. So thanks a lot to the organizers for this wonderful workshop and for asking me to give a talk. So I'll be talking on assignments, arborescences, and popularity. So let's start off with arborescences actually. So interestingly, I worked on arborescences when I was here at IISc with Demarlio and others here. So it's very nice, nostalgic to go back to arborescences here. So our input is a directed graph, and there's one special node, R, which has no incoming edge. R is the root. Every other vertex. So many times when I say vertex, I actually mean vertices other than R, the elements in the set V. So each of these vertices or elements in V has a preference order over its incoming edges, as in here. So the vertex A regards B as its most favorite in neighbor, C as its second most favorite in neighbor, and R as its worst in neighbor. So first, second, third choices. Similarly, B has a preference order over its in neighbors, so does D, so does C. R, as we said, has no in neighbors at all. What's our problem? It is to find an optimal arborescence in this graph. So what's an arborescence? It's a directed tree rooted at R. So the highlighted edges, they denote an arborescence. So what a shortest path tree is with respect to distances, and arborescence is with respect to reachability from R. So I won't keep saying R arborescence. That's what I should have been saying, because all my arborescences are rooted at R. So there's no confusion about it, I hope. So every vertex in V is reachable from R, and every vertex has a unique incoming edge in an arborescence. So what's our notion of optimality? We said we want to find an optimal arborescence. So what any vertex cares about is who is its parent in the tree. So it only cares about its incoming edge in the arborescence. And the better its incoming edge with respect to the preference order I showed in the previous slide, the happier it is with the arborescence. So how good an arborescence is this particular one? Well, A has its worst in neighbor as its parent, C has its second choice in neighbor as its parent, B and D have their best in neighbors as their parents. So is this a good arborescence? So our notion of what's a good arborescence is as follows. So it's like similar to Anupam's model. We can compare any pair of arborescences. So ask every vertex in the set capital V, where are you happier? Where do you have a better parent? So let's try to do this on the highlighted arborescence in the previous slide. So that's the one with solid edges. And there's another arborescence with dotted edges also here. So let's ask every vertex, are you happier in A, the solid one, or A prime, the dotted one? A says it prefers the dotted one, it has a better parent here. B says it's indifferent. C says it prefers the dotted one. D says it prefers the solid one. So it's 2 versus 1. B is not even interested, it's apathetic, A prime are the same to it. And among the 3 who have preferences, it's 2 versus 1. 2 prefer the dotted arborescence A and C, and D prefers the solid one.
Is there ranking for every vertex over incoming edges?
Correct. The first choice, second choice, third choice.
That's what prefers me.
Exactly. So this is, I'm sorry, this is with respect to this choice function. Sorry, please stop me if something is not clear. So I'm still carrying over these choice functions in the subsequent slides.
Are we limited to 3 choices?
No, just a small example.
These
So,
choices are uniform.
in the sense?
Like for every vertex, they have this red, blue, green color.
Not quite, no. In this example, it was all very symmetric and uniform, as you say. No, indeed. Sorry, I hope I made the model clear. So, I didn't mention again, I've just carried over the old choice functions here. Yeah?
Do we require the incoming preferences? Like, do we require a linear order on them, or?
It's a very nice question. In fact, right now I'm assuming linear order, but actually we don't. So I'll definitely come back to this point later. For now, for simplicity, I just put a linear order. Yeah, so we just wanted to ask, is this a good arborescence? Would this qualify as our optimal arborescence? And the answer is, well, the dotted arborescence is better perhaps because more vertices are happier in the dotted one than the starting one. So let's say arborescence A prime is more popular than A if the number of vertices that prefer arborescence A prime is strictly more than the number of vertices that prefer A. So the dotted one is more popular than the solid one. And let's call an arborescence popular if there's no more popular arborescence. So it's a maximal element.
So suppose we have 2 arborescence A and A prime. Except U and V, the rest have the same preferences. So for U, from A to A prime, U gets 1 better, but V gets 1
Yeah.
worse.
So we never quantify, are you happy by this much or that much? It's just a simple yes/no question. Are you happier here? Happier here. You have to choose your side.
Have the same.
Yeah. So, but we don't care. We don't care for the margin of happiness or for the magnitude of happiness. So, indeed. So this is just which side are you on? Either side with A prime or side with A.
It's not immediately clear that the popular relation is a partial order.
It's not.
You can have cycles.
Absolutely.
Voting it happens.
Absolutely. So it's different from Anupam's model. Yeah, exactly. So the audience is like way ahead of me. Arborescence A is popular if there is no arborescence A prime, that's more popular. And what we want is a popular arborescence. And yeah, so as it seems to be the case, we need to come up with a motivating application and and as Anupam said, let's be proud to be theorists. But yeah, so there is a motivating application. How real it is, I don't know. But this comes from liquid democracy, a notion in social choice where, let's say in a company, people need to come up with some choice and each of us has to vote. Let's say we have an election on where to hold the next Frontiers of Graph Algorithms workshop. And some people may say, I don't really know so much about it. Maybe I'll delegate my vote to Mohit and Mohit will cast my vote. And Mohit may say, I don't know so much, I'll delegate my vote to Anand. So each of us can delegate our vote to someone else who we think is probably more knowledgeable. So it's like out here, A says B is more knowledgeable than me. B says, no, you are more knowledgeable than me. So each person is locally saying, and so that's what is happening here. R is actually an artificial vertex we have introduced. R is not a voter. The real voters are all these guys. And each voter declares a set of acceptable representatives and has a preference order among them. So whom would I like to give my vote to? And you can't have a delegation cycle. I can't give my vote to Mohit, Mohit gives it to Anand and Anand gives it back to me. So that's not allowed. And an arborescence basically captures the entire sequence of delegations. So D has given its vote to its parent. You always give your vote to the parent in the arborescence. So D has given its vote to C, C has given it to A, and whoever is a child of R has to cast a weighted vote on behalf of itself and all its descendants in the arborescence. So that's the model. So in this arborescence, A and B cast votes, and A's vote comes with a weight of 3 because it's representing 3 people, and B casts its own vote. So the notion of liquid democracy is used in organizations. For example, it has been used in Google and some political parties too, like the German Pirate Party. So it really seeks to reform the copyright law. So the name Pirate Party, though it seems funny to us, they think that there should be free data, free information accessible to many entities and so on. So they have not used popular arborescences, but they have used liquid democracy. And we claim that a popular arborescence represents a stable way of delegating votes. And yeah, the question is, does every directed graph in our model admit a popular arborescence? So we certainly know this particular arborescence is not popular because we saw someone who defeats it, who's more popular than it. Is this popular? Even the second arborescence is not popular because it's easy to come up with yet another arborescence which is more popular than the second one, and neither is this popular. We just have to spend a couple of minutes, we can come up with a fourth arborescence that's more popular than this. So after spending a few minutes, we can come up with a conclusion that there's no popular arborescence here. For any arborescence, there's a more popular arborescence you can. And that's immediate. I'm sorry?
There is some citing, that's fine.
Yeah, exactly. So this immediately gives us an algorithmic problem to solve. Given an instance, does it admit a popular arborescence? And if there is, show it. So the background of the notion of popularity in combinatorial optimization is 50 years old. So Gardenfors came up with this notion in the setting of the stable marriage problem. So here the input is a bipartite graph. So in old times, the two sides were called men and women. Each side has preferences, strict preferences actually, over its neighbors, and we want to come up with a stable matching. So we won't really be going into stable matching, so I won't define them here. But we can come up with a notion of popularity in this setting of bipartite graphs and matchings. So any pair of matchings can be compared by asking every vertex, which matching do you prefer? Where are you happier? And a vertex always prefers the matching where it gets a better partner. It doesn't care what other vertices get matched to. It just compares its partner in matching M and matching N, and wherever it gets a better partner, it sides with that matching. And being unmatched, having no partner, is the worst option for any vertex. And a matching is popular if there is no matching, if there is no rival matching, which is preferred by more vertices than itself. And Gardenfors observed that every stable matching is popular. So in the world of bipartite graphs and two-sided preferences, the answer is popular matchings always exist. There can be cycles, nevertheless stable matchings in fact come with such nice properties that every stable matching is popular. But what about in the world of one-sided preferences? So we can think of them as students and hostel rooms. So students have preferences over hostel rooms, but hostel rooms don't care who occupies them. And so it's only the students or agents who have preferences, and we can again compare pairs of matchings, and it's only agents that prefer one matching to another. Houses have no preferences. And do popular matchings always exist in this model? Is it as nice as the two-sided stable marriage problem model? So here the colors just denote some examples of matchings I have. They don't denote preferences. The preferences are these numbers. So all three agents have the same preference order. They think of B0 as their top choice, B1 as their second choice, B2 as their third choice. So let's try to compare matchings here. So let's say we compare the green and blue matchings. So two vertices prefer the green matching to the blue matching. Is this okay? So A1 and A2 get better partners in the green matching than in the blue matching. So the green matching is more popular than the blue matching, but the red matching is more popular than the green, and the blue is more popular than red. So indeed we have a cycle here. And yeah, this instance has no popular matching. For every matching there's a more popular matching. So this motivated the algorithmic question, given a bipartite graph with one-sided preferences, does it have a popular matching? And so yeah, so there's an IISc connection. My affiliation was IISc in this journal paper. So we came up with a combinatorial characterization of popular matchings, and that allowed us to give a polynomial time algorithm for this problem. So this was ages ago. So in the setting of directed graphs, the graphs we saw in the initial slide, where vertices have preferences on incoming edges, is the popular arborescence problem sort of the equivalent to popular matching problem in bipartite graphs. So when we replace bipartite graphs with digraphs, and instead of having preferences on vertices of the other side, if we have preferences on incoming edges, somehow can we generalize, or is this the analogous problem? So this problem was actually posed by Tamas Kirai in this workshop called Emlek Tabla. I just wanted to spend a slide on this Emlek Tabla workshop. So I've never been to such a workshop before. It happens in Hungary every year. They have a theme. So in 2019 when I went there, it was matchings. And the whole workshop consists of, on Monday people arrive and they present open problems. And Tuesday to Thursday, they just split into groups, and each group just works on one open problem that they liked among the presented ones. And on Friday, people leave. So the whole workshop is there are no talks at all. Only open problems are presented, and people work like full day, Tuesday to Thursday, they work on it. And at the end of the day, there's a meeting where every group says, okay, we made some progress, we had some conjectures, we disproved our conjectures, and so on and so forth. It was a really nice workshop, and there actually Tamas Kirai posed this problem saying, given that popular matchings in bipartite graphs have been studied, why not ask this question? He didn't really have any motivating application, but interestingly some social choice people, Marcus Brill and Ulrike Schmidt-Kreplin, they were also there, and they had independently apparently come up with this problem with respect to liquid democracy. So it seemed like a very popular problem. So two sets of people had come up with the same open problem. So some of us got together, attempted it, and indeed, though we thought the popular arborescence problem ought to be in some high level equivalent to the popular matching problem in bipartite graphs, what we realized is actually no. The equivalent problem to popular matchings in the world of digraphs is the popular branching problem. A branching is a directed forest, and arborescence is a directed tree. So in a popular branching, you can have several roots. So, and just as we define popular arborescence, we can also define popular branchings. So every vertex just looks at its parent in one branching versus another branching, and to have no parent is the worst option. So this is the model equivalent to matchings, because we're not forcing every vertex to have a partner in a matching. So it's okay for a vertex to be unmatched also. Whereas in the arborescence, we were forcing everybody to have a parent. So this turned out to be the equivalent problem at the high level. And yeah, so we were 5 of us who worked on this problem. And we sort of borrowed ideas from the popular matching problem. We came up with a combinatorial characterization of popular branchings, and that allowed us to design a polynomial time algorithm for the popular branching problem. And in fact, the popular arborescence problem is a generalization of the popular branching problem. So popular branching problem has no R in it. It is just vertices and edges. We introduce this dummy vertex, make it an in-neighbor of all the other vertices, and every vertex regards R as its worst parent, worst in-neighbor. And running the popular arborescence algorithm on this problem was what enabled us to solve the popular branching problem. So we had a popular branching algorithm for this special case where R is an in-neighbor of everyone. But a typical input to the popular arborescence problem need not have R as an in-neighbor to everyone. So let's look at this example. So the red edge is the first choice, blue edge is the second choice, and this instance has only one arborescence. So by default it's a popular arborescence. There is no rival at all. Whereas if we should run the popular branching algorithm on this input, what we get is this. R is by itself and each of ABC has its favorite in neighbor as its parent. So popular arborescence and popular branchings are different, and basically in the popular arborescence problem, reachability from R is more important than popularity. So we are asking the arborescence only to be compared to other arborescences. So that way we are weakening the condition. A branching has to compete against every branching. However, we are being stricter in the structure we are asking that the structure should be an arborescence. Everybody should be reachable from R, whereas branching had no such rule on it. So this, in fact, motivated us to think, if branchings are the analogous structures in digraphs to matchings in bipartite graphs, then what is the analogous structure in bipartite graphs to arborescences? Yeah, and the answer is assignments. So an assignment is a perfect matching. Everybody has a partner. So no perfect matching defeats a popular assignment. It can lose to smaller matchings. So popular assignment is a perfect matching that is popular within the set of perfect matchings. Is it okay? Yeah. So given a bipartite graph, does it have a popular assignment? And our popular matching algorithm does not solve this. And this is in fact a generalization. Just as we put a dummy root and said the popular arborescence problem is a generalization, here also we can put some dummy vertices and every matching becomes a perfect matching. So this is a generalization, and the old algorithm from 2007 does not solve this problem. So neither the combinatorial structure carries over nor the algorithm. Yeah, so we go back to the stable marriage setting. So the question of, does a graph admit a popular maximum matching? So this was considered in the stable marriage setting. So popular maximum matching is just a maximum matching that's popular within the set of maximum matchings. And in fact, the proof, so in fact every stable marriage instance admits a popular maximum matching, and the proof is algorithmic. We'll actually construct such a popular maximum matching, and that's why this nice idea, replace every edge in the given graph by a whole host of edges like this. So let's replace it with n parallel copies. So I have marked each copy with a different color, and there's tension between the two sides A and B. A says, well, red is my favorite color, then comes blue, then comes green, and so on. So any red edge is better than any blue edge. Within red edges, it is as per its original preference order. Within blue edges, it is as per its original preference order. But as far as comparing red and green edges, any red edge is better than any green edge. Whereas vertices on the other side, B, have preferences the other way around. What color A says is its worst color becomes its best color. The order is just the other way around. So we want tension between the two sides. Is this okay? So given a bipartite graph, let's replace every edge in the given bipartite graph with this. So n is the cardinality of the size of set A. So we construct a multi-graph like this, and a stable marriage in this colorful multi-graph actually is a popular maximum matching. So the Gale-Shapley algorithm in this colorful multi-graph. So there are always stable matchings. So stable matchings always exist, hence popular maximum matchings always exist. So in the two-sided preferences world, preferences are strict here and two-sided. We have a happy ending to this story. Popular maximum matchings always exist, and they're easy to find. We just construct this colorful graph and run Gale-Shapley algorithm on it. But does this give us any ideas for the one-sided setting. So our final goal is to solve the popular arborescence problem. Hence, so we took this detour via popular assignment problem, and then we took a further detour saying that we know how to solve it in the two-sided world, but can we somehow make this work in the one-sided world? Yeah, so this idea of colorful graphs, can we borrow this idea? Yeah, so instead of coloring edges as we did in the stable marriage setting, let's use a color, or let's call it level because I'm just using numbers here. Let's use a level function on houses. So houses are the vertices that have no preferences, and let's come up with a level function on houses. And for any agent, so let's come up with this function L star A, which is the highest level of any of its neighbors. So L is a function on houses, so every house gets some number, and agent A, let's look at A1. So these are its preference orders. A1 thinks this house is its most favorite house, this is its second most favorite house, this is the third most favorite house. But the levels of these houses are, this has level 2, so green denotes level 2, blue denotes level 1, red denotes level 0. So L star of A1 is 2. A2 has in fact no house in level 1, its neighboring houses, so these are the top choices, this is second choice, all its neighbors are in level 0 and 1. So 1 is the highest level at which it has a neighbor. So the L star function is defined like this.
Sorry, what are houses? What do you mean?
They are the vertices in the bipartite graph without preferences.
Okay.
So we're back in the bipartite world setting with one-sided preferences. So agents on one side, they have preferences.
Right.
So agents are students. Houses are their hostel rooms. So when you enter, maybe you have to give some preference on, or let's say you're a first year student. At the end of first year, you can change your room. You have a preference order on rooms.
Right.
So houses are rooms. They have no preferences.
Right.
We have not yet discussed how to assign them level, right?
No, that's the whole algorithm. I'm just saying, if there is a level, sorry. So, if there is a level function on houses, I'm somehow coming up with yet another function called L star. So the question was, who came up with this level function? Who decided that this house has level 2, this house has level 1? Nobody. But I'm saying, if someone had come up with a level function, then I'll come up with this L star function, which is like this. Yeah. So again, assuming we have a level function, let's define a corresponding subgraph. And in the subgraph, a vertex, an agent, keeps edges only to its favorite highest level neighbors. And it also keeps edges to its favorite one level lower, that is highest minus 1 neighbors, if it prefers them to all its highest neighbors. So is this okay? So let's just go back to this example graph. So A1's top choice neighbor was this room, but its level is too low. This is level 0, this is level 1, that's level 2. It's not in the top 2 levels for A1. So there is no way it would keep this dashed edge in the corresponding subgraph. It only looks at highest level, so it keeps the edge to the green house. It's ready to go one level lower to level 1, but it's a third choice. It in fact dislikes this room compared to that room. So it keeps only one edge in the subgraph. This vertex on the other hand, it prefers, so it has neighbors in level 1, one neighbor in level 1, two neighbors in level 0, and it prefers the level 0 neighbors to level 1 neighbor. So it keeps all the 3 edges in the subgraph. So we're just defining a subgraph.
So could you explain the choice of the subgraph?
Yeah. So given a level function, I'm defining the subgraph.
Okay.
So the subgraph is defined as every agent looks at the highest level at which it has a neighbor.
Okay.
And in that highest level, it keeps edges only to its most favorite neighbors.
Okay.
And it's ready to look at one level lower also. And there it keeps edges to its favorite neighbors, provided they are strictly more preferred to these neighbors.
Okay.
So I think a very good analogy here would be when we are booking flight tickets. So we may have preferences over our timings or airlines or so on. But when we get a list of it, we always go for the cheapest option. So this is like, exactly, in fact, this is like an auction algorithm actually. So the higher the level, the cheaper it is. So you have your preferences, but all those preferences are secondary compared to the cost of the ticket. So we'll always look at the cheapest bucket of tickets, and among them, the candidates we are ready to buy or get matched to are your most favorite cheapest level tickets, and you're ready to go one price level higher, that is one level lower. So levels are like inversely corresponding to prices. You're ready to go one level lower, you're ready to pay one extra, to go to one extra more expensive bucket, provided it's a strictly better flight. It has a better timing or better airline or so. So this is that.
So it's basically only 2 levels are popular.
Only 2 levels. So it's not even that if I have a level 10 neighbor, nobody in 9 but someone in 8, 8 does not become eligible. It's only 10 and 9. If you have nobody in 9, nobody in 9.
Sure.
Yeah, sure.
In that example, you've kept the edges to all of the ones in one, right? For 8.
For 8 to, yes. This guy has no one. It has a single neighbor in the subgraph.
But you said favorite L star, but that means all of them at level 1, level 0.
So these are level 0, they are the favorite ones.
All of them.
All of them.
And the
Sure.
same will be true for the highest level.
Yeah, if you have multiple favorites, you keep adjust to all of them. And you're ready to go one level lower, provided they're strictly better than these. So these in your absolute rankings could have had a really bad rank, but they are ready to come cheap, so that makes a difference. So yeah, so this is really our characterization theorem here. So G has a popular assignment if and only if there exists a level function. I still haven't made clear how we find this level function, but at least we have a way forward. If there exists a level function such that this subgraph admits a perfect matching, such a perfect matching will be a popular assignment. So the whole job is to come up with this level function. But once we have a level function, we know how to solve the problem. So what is a good level function? A level function is good if the corresponding subgraph. Once you have a level function, the subgraph is immediate. If the subgraph has a perfect matching, the original graph has plenty of perfect matchings, but the subgraph need not have one. If it has one, that will be a popular assignment.
So the level function can be anything?
Yeah, level function can be anything.
It just has to satisfy this.
So there is nothing that's stopping any level function. You can say, in fact, L of B is 0 for everyone. That's a valid level function. But the corresponding G sub L need not admit a perfect matching. So in fact, we'll start off with that level function. So our algorithms is the same group that we worked in Emlek-Tadla on the popular branching problem. So find the right level function. That's the problem. And our algorithm is, let's start with L of B equal to 0 for every house. Compute a maximum matching. So how is the graph G sub L for this level function? Every agent has edges only to its most favorite houses. If this subgraph has a perfect matching, that's the best possible story. Every agent gets his favorite house. If it's not, then for every unmatched house, so the maximum matching is not perfect, there are unmatched houses. We assume the cardinality of the two sides are the same because the graph has a perfect matching. So there are unmatched agents, there are unmatched houses too. Each unmatched house increases its level. And if the level of a house becomes n, then there's no popular assignment. Else, if all levels are less than or equal to n minus 1, go back, change your subgraph, again ask for a maximum matching. If it's perfect, then story over. Otherwise, increase the levels of unmatched houses and so on.
So the theorem, the characterization you gave on the previous slide, is that like, are you proving this via some kind of duality?
Of course, yes. This is the dual certificate, the level function. Exactly. So the question was, are you proving it by LP duality?
Is it clear that perfect matching is a popular assignment? Or
Any perfect matching, here is a popular assignment. But not every popular assignment needs to come in one particular GL. So every popular assignment has its own level function. It appears as a perfect matching in its GL.
no, sorry, my question was, is the last line should be obvious, like a perfect matching is a popular assignment?
because it will have a dual certificate which will be given by this. So I'll just come to it in a couple of slides. Sure. Any perfect matching in G sub L will be a popular because there will be a dual certificate to ratify it. So this is a dual function. Yeah, so in fact this is what I call an auction algorithm. So one Japanese professor in fact gave me this analogy of this is what happens in an auction. Initially all houses, let's call them, they are being auctioned. They come at the expensive price. They want to be sold at that price. However, enough people are not interested in certain houses, then they have to lower the price. Then a house that you didn't find interesting starts looking interesting because the price is lower. And then finally at some point, well, there's no way you can reduce the price to 0, so then we say there's no popular assignment. Yeah, so going back to what someone asked me in the beginning, this algorithm works for partial order preferences and surprisingly, even if there are cycles in preferences, all we need is pairwise comparisons. And this is true in real world, right? You may like house 1 more than house 2 more than house 3, and house 3 more than house 1. So it's very hard to come up with a total order on all houses. So all we care for is, given any pair of houses, an agent says, I prefer these two, or both are the same to me. And this algorithm works. Well, you don't even need transitivity. And its correctness is shown by the LP method, as Anupam asked. Yeah, so for any perfect matching, there's a corresponding edge weight function which takes values in +1, -1, 0, depending on, well, if you like B more than your partner, then the edge between A and B gets weight 1. If you like B less than your partner, the edge weight is -1, I'm sorry. And if it's indifferent, if you're indifferent between B and your partner, the edge weight is 0. And yeah, so this is dual to the max weight perfect matching LP. So an assignment is popular if and only if it is a max weight assignment under this edge weight function. And this is the dual LP, and there is in fact a simple enough claim that shows this LP has nice optimal solutions. It's totally unimodular, so it has integral solutions. Moreover, all these YA, YB values are just in this set. And what our algorithm is looking to find is the absolute value here. So the level function we assign is actually the absolute value of this YB function. And I will not really go into this, but our algorithm finds, in fact, a minimum such dual certificate. So if the graph has popular assignments, well, then each popular assignment has this kind of a dual certificate. And let's take any house B, the least possible absolute value of YB it gets in any dual certificate, our L of B will be equal to that. So it keeps levels as low as possible. And even when in our algorithm the L of B value goes to n, it means there is no dual certificate possible, hence no popular assignment possible. So the proof of correctness is by LP duality. We'll go into a little more detail in the arborescence case. I'm sorry, I think I'm running out of time already. But let me quickly go back to the arborescence problem. So we just mimic what we have done in the assignments case. So let's use a level function on the edge set. And for every vertex, let's define this L star function, which is the highest level among the incoming edges. And let's define a corresponding subgraph G sub L. So incident to every vertex are its favorite incoming edges in the highest level at which it has some in neighbors, and is ready to go one level lower, provided these incoming edges are strictly preferred to the highest level edges. So let's go back to our old example. So if we come up with such a level function, then in fact the corresponding subgraph G sub L is the original graph itself. And analogous to the popular assignment case, we have such a theorem that G admits a popular arborescence if and only if there is a nice level function. Well, there we just said GL admits a perfect matching. Here it becomes a little more demanding. GL admits not just an arborescence, but when we ignore the edge directions, and look at it as a tree. It's a minimum spanning tree in the underlying graph G, where the edge costs are given by levels. So it's a little more involved theorem than the assignments case. So the connection between assignments and arborescences is basically intersection of matroids. That's the intersection of two partition matroids, so life was simpler there. Here it is intersection of partition matroid and graphic matroid. So this is where the graphic matroid is.
So can you do intersections of partition matroids and
Anything it works. I didn't want to get into that, but the same algorithm works. It's exactly the same. So this is a generalization of the popular assignment. That was the special case of two partition matroids that had more structure. So in fact we struggled a lot to generalize from assignments to arborescences. But it was finally a very neat characterization. And yeah, such an arborescence will be a popular arborescence. Any arborescence in GL which satisfies this desired condition. So suddenly your levels become your costs and you want the undirected tree to be an MS tree. Yeah, so going back to this, we said for this level function, the corresponding G sub L is a graph itself, and in fact, this arborescence does satisfy our MST condition. So our whole problem now is find the right level function on the edge set such that this subgraph admits a desired arborescence, or we have to decide there is no such level function. So it's similar to the assignments case, but things are a little more involved here. Nevertheless, I hope our algorithm is almost as simple. So this is joint work with Kaz Makino, Ildi Schlatter and Jimmy Yokai. So we start off as before. Let's take level of every edge to be 0, construct the corresponding subgraph, and let's find an L greedy branching here. So it has as many level 0 edges as possible, subject to this as many level edges, level 1 edges, and so on. So if this L greedy branching is a spanning tree and moreover an MST in the underlying undirected graph, then great, return B. Else we have to increase some levels. So let K be the least level with an edge that violates the undirected tree being an MST. Will increase the levels of all these violating edges in level K. So we have to be a little more careful here when compared to the bipartite case, the popular assignments problem, but this is it. So this is almost in the same spirit as that, but little extra care. We have to find an L greedy branching. We have to check it's a minimum spanning tree with respect to the level function in the underlying undirected graph. And then we happily increase the levels of all unmatched houses. Here we take only the least level with these violating edges and increase their level. So I wanted to do a couple of examples. Do I have the time? So yeah, so this was our starting example that did not have a popular arborescence. So let's run our algorithm on this. It should give the answer no. So we start off with all edges are at level 0. Then G sub L by definition has only the red edges as this. And then let's find a greedy branching. So I took the edges A, B and C, D. Now all blue-green edges are violating because forget minimum spanning tree. I mean there is no edge that connects R to A in this branching, no edge that connects R to C or A to C, so on. So we increase that level. And now G sub L has all red and blue edges. Because blue and green edges have level 1, we have increased their level. Red is still at level 0. And the definition of GL says highest level edges take your favorite ones, one level lower take them if they are strictly preferred. So it's only the red and blue edges that are there in the subgraph. So that's the subgraph. And now let's again take a greedy branching. The green edges are violating because there's no path in the there's no spanning tree to begin with. There's no path in the forest between the root and any of the vertices. So we increase the green level to 2. And now the subgraph consists of green and blue edges. We can just go through this exercise. Red edges are violating, so we increase their level. Then the graph consists of red and green edges, and blue edges are violating. So in fact, we can see the cycle. So we start with red-blue subgraph, then blue-green subgraph, green-red subgraph, and back to the blue-red subgraph. And finally, at some point, the level of green edges becomes 4, and that's too high for us, and the algorithm says there's no popular arborescence. And I thought I'd do one more example where there is a popular arborescence. It's very similar to the previous example, except that the edge RD is missing here. And we again start off with, let's set all edge levels to be 0. GL has only the red edges. So this is the starting GL. Then we increase the blue-green levels to 1. So this is similar to what we saw earlier, except that now at this point, because D has no green edge in it, G sub L at this stage will have all blue-green edges and the red edge CD. So now we take a greedy branching, and then these two edges in fact violate the MST-ness of the undirected graph. So their edges, they are the violating edges, only they get increased. This edge does not increase its level because in the undirected graph, there's already a red edge between C and D. This is like the min-max path that we were hearing yesterday in Tachopol's talk. So, yeah, so this graph has a desired arborescence. So when we look at this branching B, its underlying undirected tree is an MST, and in fact there's another possible output also. So this, both B and B prime are popular arborescences in our starting graph. So I just wanted to talk a little bit about how this LP duality allows us to show the correctness of our algorithm, but I guess I have no time, so this is the arborescence polytope. Rank for any subset of the H set, rank of S is the size of a largest acyclic subset of S, and yeah, an arborescence is popular if and only if the optimal value of this LP, it's a primal LP, is 0. This is a dual LP, and there is a nice dual certificate that is a chain, and what our algorithm is doing is hunting for a nice chain. And these level functions, they allow us to define this chain. So whenever we return an arborescence, that's a popular arborescence as ratified by this nice chain. And when our algorithm says no, we can again argue that indeed there is no popular arborescence. Again using these chains, the dual certificate. That's it. Thank you. Yeah, and thanks to so popular assignments were with Tamash, Ildi, Yannick and Ulrike. Popular arborescences were with Kaz, Ildi and Yuyoko.
Are there any questions?
So one can have weighted version, right? Vertices have weights and you can define.
We don't know how to solve that question. A very nice question. Yeah, indeed. And we know how to do it. But in the assignments or arborescences world, I tried a lot actually, and I sort of have not made any progress.
Is there actually from this? Is there any links to notions of equilibrium, Nash equilibrium, with the popularity? And do they have any connection somehow? I mean, this notion of being. Can one sort of think in that way of you choosing strategy which is more popular?
I don't know, refer it to Siddharth. Do you see any connection?
These are like very utilitarian. So like what this is bit of a different beast. Like many settings you do have equilibria, whereas here you do have like even in simple algorithms it's popular, right? So I would say yeah, I mean there is a best response flavor to it, but like fundamentally I would say they're different.
Yeah, and also this is closely linked to this Condorcet winner in social choice theory. So
yeah, it's more voting literature than
exactly.
Yeah.
So this is more of social choice connection than the direct AGT connection.
There are no more questions. Let's thank the speaker again.
Thank you so much.
So, quick announcement for people staying in JVH and Faisala. Please collect your breakfast coupons for the next 3 days from the reception, please.
And also one small announcement, we have a open problem Google document which is begging to get filled. Please contribute over there so that we can discuss tomorrow as well. We will share.
Thank you. Thank you. Thank you.